Hello there and welcome to Science for Sleep, where curiosity gets cozy, the universe lowers its voice a little, and even the strangest objects in space are allowed to arrive at a calm and reasonable pace. Tonight, we explore one of the strangest worlds ever found beyond our solar system. It is called Poltergeist, which is already a name that feels as if astronomy briefly left the lights off in a haunted house and then decided to take notes. But Poltergeist is not a ghost in the usual sense. It is a planet. A real planet. A world with mass, an orbit, gravity, and a place in the sky. What makes it so strange is where it lives. It circles a dead star, a pulsar called PSR B1257+12, sometimes known by the name Lich, which is very fitting because a pulsar is not a warm, gentle star like our Sun. It is the crushed core left behind after a massive star died violently. So tonight's story begins not with golden sunlight or blue oceans or a quiet morning on another Earth, but with a planet moving around the remains of a star that should have ended the story long before any planets had the chance to be there. Before we go farther, I would love to know where you're listening from tonight. Are you somewhere bright and awake, with traffic outside and the day still carrying on? Or are you tucked into a darker corner of the world, where the room is quiet and the clock has started to feel softer? And if you feel like sharing it, what time is it for you right now? It feels appropriate to ask, because the way astronomers found Poltergeist was through timing, not by seeing the planet directly, not by taking a pretty photograph, not by watching it pass across the face of its star like many other exoplanets. They found it by listening to the tiny changes in a dead star's pulse. That is a strange thing to think about. A world discovered not because it shone, but because it tugged. A planet revealed by the way it made a cosmic clock arrive a little early, then a little late, then early again. Like a quiet hand disturbing the rhythm of something much larger. If you find this kind of journey soothing or interesting, or simply a nice way to let your mind wander somewhere far from the noise of the day, I would be grateful if you liked the video and subscribed. It helps this calm little corner of science reach more tired minds, more curious people, and more listeners who might enjoy drifting through the universe without being shouted at by it. And tonight, we may need that calm, because Poltergeist's home is not exactly a peaceful suburb of the galaxy. It is not the sort of planetary system where you imagine soft sunsets, mild weather, or a small alien creature politely wondering what clouds are. This is a place shaped by death, radiation, extreme gravity, and a star that spins so quickly it seems almost impatient. Yet somehow, a planet is there. Not just any planet, but one of the first confirmed planets ever discovered outside our solar system. Long before astronomers found thousands of worlds around ordinary stars, this strange dead star system quietly opened the door. So, settle in, let your thoughts slow down, and imagine that we are moving away from Earth. Not quickly, no rush. We pass the moon with its familiar grey face. We move beyond Mars, Jupiter, Saturn, and the long, dark distances of our outer solar system. The sun becomes smaller behind us, first a blazing coin, then a bright star among other stars. Eventually, even our familiar constellations begin to lose their shapes, because those shapes are only what the sky looks like from home. We are heading toward a point in the constellation Virgo, where a dead star spins in the darkness. You would not notice it with your eyes. It does not glow warmly like a normal star. It does not sit there calmly making daylight for its planets. It is a neutron star, one of the densest objects in the universe, the leftover core of a star that once ran out of fuel, collapsed inward, and exploded outward as a supernova. The outer layers were blasted into space. The core was squeezed down into something only about the size of a city, but heavier than the sun. That idea is difficult to hold in the mind without it slipping away. A star's core compressed until matter behaves in ways that ordinary experience cannot prepare us for. If you could scoop up a spoonful of neutron star material which you absolutely should not try to do. It would weigh about as much as a mountain, or more, depending on which mountain is having a particularly heavy day. Neutron stars are the universe's answer to the question, how much matter can you pack into one place before nature starts looking deeply uncomfortable? And when such a star becomes a pulsar, it sends beams of radiation out from its magnetic poles. As it spins, those beams sweep through space. If Earth happens to lie in the path of the beam, we detect a pulse each time it swings past, like the flash of a lighthouse, except the lighthouse is made from the remains of a dead star and rotates many times each second. Not exactly something you would want guiding ships home, unless the ships were very far away and made of equations. PSR B1257+12 is a millisecond pulsar, meaning it spins extremely fast. Its pulses are so regular that astronomers can treat them like the ticks of a cosmic clock. This regularity is important. A normal star can flicker, flare, swell, and blur its signals in many complicated ways. A pulsar, when it is stable enough, can be timed with astonishing precision. Each pulse arrives at a radio telescope after crossing space for years and years. If nothing disturbs the pulsar, the pattern stays steady. But if something orbits it, something with gravity, even something as small as a planet, the pulsar will move slightly around the shared centre of mass. It does not sit perfectly still, it wobbles. That tiny motion changes the arrival time of the pulses. Sometimes the pulsar is a little closer to us in its orbit, so the pulse arrives slightly earlier. Sometimes it is a little farther away, so the pulse arrives slightly later. We are talking about very small changes, the sort of differences that would be hopeless in everyday life. If someone said your tea was ready a few millionths of a second late, you would probably forgive them. But in pulsar astronomy, those tiny changes can reveal entire worlds. That is one of the reasons Poltergeist feels so special. It was not found around a friendly sun-like star. It was not found by the methods that later became familiar in exoplanet science. It was found because a dead star was too precise to hide the disturbance. The planet was invisible, but its gravity left fingerprints in time. There is something almost funny about that. In the quiet way space can be funny. A planet named Poltergeist was discovered because it was making tiny disturbances, shifting the furniture of a pulsar's timing by amounts only a radio telescope and a patient astronomer could notice. In old stories, a poltergeist is a noisy ghost, something that knocks on walls or moves objects when nobody's looking. In this system, the name works unusually well. Poltergeist does not knock on walls, at least not any walls we know of, but it does tug on the dead star it orbits. It leaves a disturbance. It announces itself through a pattern that should have been perfectly regular, but was not. And this is where the story becomes even stranger. When the first planets around PSR B1257+12 were reported in the early 1990s, astronomers were still at the beginning of the exoplanet era. Today, we are used to hearing about planets around other stars, hot Jupiters, super-Earths, mini-Neptunes, ocean worlds, lava worlds, planets so close to their stars that their years are shorter than a long weekend. The catalogue has become crowded, but at the time, the idea that planets could be confirmed around another star was still fresh and difficult. Many scientists expected the first clear examples to appear around stars like the Sun. That seemed sensible. Our own planets orbit a normal star, so perhaps other planets would first show up around similar stars. Instead, one of the first proven planetary systems was found around a pulsar. It was like searching for a garden and finding one growing in the ashes of a burned-down house. Not impossible perhaps, but surprising enough to make everyone check the measurements more than once. Poltergeist itself is a super-Earth, larger in mass than our planet, though not a giant like Neptune or Jupiter. It orbits close to the pulsar, completing a year in just over 2 months. Try to picture that for a moment. On Earth, a year gives us time for seasons, holidays, birthdays, long stretches of weather, and the usual human business of wondering how it is already July. On Poltergeist, one trip around the dead star takes about 66.5 Earth days. If you could stand there, which you cannot for many very sensible reasons, the calendar would race by. A person who was 10 years old in Poltergeist years would still be less than 2 Earth years old, though again there would be the small issue of radiation, no breathable air, and the general lack of a comfortable place to put a birthday cake. Still, the orbit tells us something important. This planet lives close to its pulsar, close enough that it must experience a sky nothing like ours. There would be no warm yellow sun hanging overhead. A pulsar is not bright in the same ordinary way. It sends out intense radiation, including radio waves, X-rays and streams of energetic particles. Depending on the planet's atmosphere, if it has one, and its surface conditions, the environment could be harsh beyond anything familiar on Earth. The phrase zombie planet is not a formal scientific category, of course. You will not find a neat shelf in astronomy labelled zombie planets, between gas giants and slightly rude asteroids. But as a description, it makes sense. Poltergeist seems to belong to a system that came after death. Either it somehow survived the violent death of the original star, which would be remarkable, or it formed later from debris left behind after the supernova, or from material pulled in during the pulsar's later history. In either case, this is not a normal childhood for a planet. It did not simply grow in a peaceful disk around a young star and spend billions of years enjoying predictable sunlight. Its existence is tied to catastrophe. The old star that came before the pulsar would once have been massive, bright and short-lived compared with the sun. Massive stars spend their fuel quickly. They burn intensely like someone who enters a quiet room and immediately turns on every lamp, opens every window, and starts rearranging the furniture. They do not last long on cosmic timescales. Eventually the core can no longer support itself. Gravity wins, the star collapses, and the outer layers explode into space. That explosion, a supernova, is one of the most violent events in the universe. It can shine brighter than entire galaxies for a short time. It throws heavy elements outward. It can destroy nearby worlds, strip atmospheres, melt surfaces, and scatter material across space. So when we find planets around the collapsed remnant, we are forced to ask a very direct question. How did they get there? Were they survivors, somehow battered but still present after the explosion? Or were they second-generation planets, built from material that gathered after the star had already died? Neither answer feels ordinary. If Poltergeist survived, then it endured a stellar death that should have been devastating. If it formed afterward, then planets can be born in places we once might have dismissed as too ruined, too violent, too strange. This is why the system matters beyond its eerie name. It changed expectations. It showed that planet formation is not limited to calm nurseries around young stars like the sun. Nature can assemble worlds in unexpected places, even around objects that seem more like endings than beginnings. And that is one of the quiet lessons of astronomy. The universe does not always separate beginnings and endings as neatly as we do. A supernova is the death of a star, but it also spreads the ingredients for future stars and planets. A pulsar is a remnant, but it can still have companions. A dead system can contain or create new structure. Even in the aftermath, gravity keeps working, dust still collides, debris can settle, orbits can form. The universe is very good at reusing material, rather like someone who refuses to throw away a box because it might be useful one day, except the box is made of exploded star. It is also worth noticing how quiet this discovery was in a sense. Not quiet scientifically because it was a major event, but quiet in the way it reached us. There was no image of a blue-green world, no dramatic silhouette against a glowing star, no little dot moving in a telescope picture. The evidence came through timing, pulse after pulse, measurement after measurement, a pattern, then a variation, then an explanation. This is one of the most patient forms of discovery. It asks astronomers to trust the rhythm, then notice when the rhythm is not perfect. It is like hearing a clock in another room and realizing, after listening for a long while, that something is gently pulling the clock back and forth. Most of us live surrounded by timing errors all day. Late buses, delayed replies, alarms we ignore, ovens that claim to be preheated when they're clearly being optimistic. But in pulsar timing, a tiny delay can be a planet. A small shift can mean an unseen world is moving through the dark. Poltergeist star PSR B1257+12 also has company beyond Poltergeist itself. There are other known planets in the system, with names that continue the undead theme. Draugr, a much smaller world, and Phobitor, another super-Earth-sized planet, share this strange family. Their names sound like something you would not want to find written on a cabin door during a thunderstorm, but in astronomy they help us remember that these are not ordinary planets around an ordinary star. They are pulsar planets, and pulsar planets are rare. Most exoplanets we know orbit main sequence stars, red dwarfs, sun-like stars, or evolved stars that still shine in more familiar ways. Pulsar planets are different because the host is a compact remnant, and the environment is extreme. They force us to think about planet formation under conditions that are not comfortable, not simple, and not especially friendly to life as we know it. If Earth is a house with a warm lamp in the window, Poltergeist is a stone in a storm beside the remains of the lamp after it exploded. Yet it would be too simple to treat Poltergeist only as a horror story. It is strange, yes, hostile probably, but it is also a triumph of measurement and imagination. No spacecraft has gone there. No telescope has resolved its surface. We do not have pictures of mountains, craters, plains, or anything else that might exist there. And still, we know it is present because physics gives us a way to listen. The planet's gravity affects the pulsar. The pulsar's beam reaches Earth. Radio telescopes record the pulses. Human minds examine the tiny changes. From that chain, a world appears. This is the kind of thing science does at its best. It turns small clues into large realities. It lets us say, carefully but confidently, that around a dead star in Virgo, a planet is circling. There is a gentle irony here too. The first confirmed planets beyond the solar system did not immediately give us a second Earth. They gave us worlds around a corpse of a star. If the universe was trying to introduce us to exoplanets, it did not begin with the comforting option. It began with a reminder that planets are more varied than our expectations. We had imagined other solar systems as perhaps neat versions of our own, with stars, rocky planets, gas giants, and maybe something familiar enough to make us feel less alone. Instead, the early evidence pointed to a place where a stellar death had already happened and planets still moved through the aftermath. It was unsettling, but useful. It widened the search. It told astronomers that planets might be common in ways we had not expected, and that we should not only look where things seem friendly. Sometimes the most important clue is hiding in the least comfortable place. As we move through this story, we will return again and again to that central puzzle. How can a planet exist around a pulsar? What would its sky be like? What did the original star do to the system? Did Poltergeist form from ashes, or did it endure the explosion in some altered orbit? What does it mean for a dead star to keep time so well that its planets can be discovered by the slight trembling of its pulse? These questions do not need to be rushed. They can unfold slowly, one at a time, the way a radio signal from deep space arrives after a long journey and waits to be understood. For now, it is enough to hold the scene in mind. A dark region of the sky, a neutron star spinning faster than anything in daily life should spin, beams sweeping outward, a planet circling nearby, unseen but not silent, tugging on the clock that revealed it. And maybe that is why Poltergeist is such a fitting place to begin a sleepy journey through extreme astronomy. It is not loud in the way its name suggests. It does not leap out at us. It does not glow like a lantern. It makes itself known through patience, through repetition, through timing. It is a ghostly world only because we cannot see it directly, and a zombie planet only because its story belongs to the afterlife of a star. But it is real, and reality is often stranger than the names we give it, so let your eyes rest if they want to. Let the room around you become a little less important for a while. Somewhere far away, PSR B1257+12 is still spinning. Its pulses are still crossing space. The signal itself is the first thing to understand, because before Poltergeist was a name, before anyone spoke of zombie planets or ghostly families, there was a pulse. Not a heartbeat in the living sense, of course, though it is hard not to hear it that way once you know the story. PSR B1257+12 is the kind of object that seems to make the universe feel both very old and very precise. It is a dead star, but not dead in the quiet, settled way a cold stone is dead. It is active, it spins, it beams. It keeps time with a strictness that would make even the most punctual railway inspector feel slightly underprepared. And because it keeps time so well, the smallest disturbances around it can become visible to us. Not as light, not as a photograph, but as tiny errors in the arrival of its pulses. A normal star is a furnace, a glowing sphere of hot gas held together by gravity and supported by the energy made in its core. Our sun is like that. It shines steadily enough that we build days, seasons, weather, calendars, and afternoon walks around it. PSR B1257+12 is not like that at all. It is what remains after a massive star's ordinary life has ended. Long ago, the star that came before it burned through its fuel, lost the long fight against its own gravity, and collapsed. Its outer layers were blasted into space in a supernova, while its core was crushed into a neutron star. That core became an object so dense that the usual examples always sound as if they have escaped from a science classroom and wandered into a fairy tale. A city-sized object with more mass than the sun, a spoonful of material that would weigh more than a mountain. A star reduced to something small enough to sit inside a large city, if cities were built to contain objects that could flatten them just by existing. But PSR B1257+12 is not only a neutron star, it is a pulsar. A pulsar is a rotating neutron star with strong magnetic fields and beams of radiation that sweep through space. The usual comparison is a lighthouse, and for once the usual comparison works rather well, as long as you remember that the lighthouse is made of ultra-dense matter, is spinning many times each second, and is not somewhere you would stop for a holiday. The beams do not shine in all directions evenly. They sweep around as the star rotates. If one of those beams happens to point toward Earth during each rotation, our radio telescopes detect a pulse. Then another, then another. The star seems to blink, not because it is actually switching on and off, but because its beam is crossing our line of sight. This is where Lich enters the story. Lich is the name given to PSR B1257+12, and it fits almost too well. In fantasy stories, a Lich is an undead being, something that should have died but continues on in a changed and unsettling form. In astronomy, names are often less dramatic than the objects deserve. A galaxy may be called NGC something, a nebula may be given a catalogue number, and a world may be known by a string of letters and numbers that sounds like a password someone forgot to make friendly. But Lich is different. It tells you something immediately. This is a dead star that still acts. It has no gentle daylight. It has no warm photosphere like the sun. It has a crushed core, a magnetic field, and a pulse that crosses space with astonishing regularity. If the sun is a hearth, Lich is the ticking machinery left behind after the house burned down. And around this undead star there is a family. That is the part that still feels strange even after saying it more than once. Planets orbit Lich. Not one lonely fragment, not only a cloud of debris, but a small system of worlds. The innermost known planet is Draga, a tiny terrestrial world much less massive than Earth. Farther out is Poltergeist, the planet at the centre of our journey. a super-Earth with about 4.3 times Earth's mass. Beyond it is Phobietor, another super-Earth, slightly less massive than Poltergeist. These names continue the ghostly theme, as if the whole system were trying very politely to warn astronomers that this was not a regular neighbourhood. Draugr comes from old stories of the undead. Poltergeist suggests an unseen disturbance. Phobietor is tied to dreams and fear. It is a planetary family that sounds like it should be introduced by a creaking door, and yet the science behind it is careful, measured, and beautifully exact. The family is compact compared with our own solar system. Draugr circles the pulsar in about 25 Earth days. Poltergeist takes about 66.5 days. Phobietor takes about 98 days. Their orbits are all much closer to their dead star than Earth is to the Sun, although distance around a pulsar does not mean what it means around a warm star. Around the Sun, distance helps decide how much light and heat a planet receives. Around Lich, distance also means exposure to the pulsar's radiation, its particle wind, and the strange environment created by a spinning neutron star. It is not simply a question of standing under a brighter or dimmer lamp. It is more like deciding how close you want to sit to an engine that is also a lighthouse, a magnet, and the remains of a stellar explosion. The correct distance, for comfort, is probably somewhere in another star system. Still, the planets move there with the calm obedience of gravity. That is one of the useful things about gravity. It does not care whether a place seems spooky. It does not object to names. It does not pause and say, actually this system feels a bit haunted. If there is mass and motion, gravity begins its work. A planet falls around its star, missing it continuously, tracing out an orbit again and again. Around Lich, that motion is what makes the pulse imperfect from our point of view. The pulsar is not nailed to the centre of the system. Nothing in space truly is. Each planet tugs on it. The pulsar and the planets all orbit their shared centre of mass. Because the planets are small compared with the neutron star, Lich's motion is tiny, but tiny is not the same as zero. And with a clock this precise, tiny can be enough. Imagine a clock on a table at the far end of a very long hallway. The clock ticks exactly, with a rhythm so steady that you begin to trust it completely. Now imagine that the table is being moved toward you, and away from you by a barely visible amount. The clock itself is still ticking properly, but the sound reaches you a little early when it is closer and a little late when it is farther away. If you listened carelessly, you might miss it. If you listened with the right instruments, and if the clock were precise enough, you could work out that something was moving the table. That is the basic idea behind pulsar timing. The pulses from PSR B1257+12 cross the space between the pulsar and Earth. When the pulsar is nudged by orbiting planets, the distance those pulses must travel changes slightly. That changes their arrival times. The planet remains unseen, but its gravity has written itself into the schedule. This is why the pulse from Lich is so important. It is not just a signal, it is a measuring tool. A radio telescope does not receive it as a spooky sound, though turning it into one would certainly make for a memorable evening. It receives radio energy, records the timing, and builds a long record of pulse arrivals. Astronomers compare what they expect with what they observe. If the pulses arrive exactly as predicted, the model is probably missing nothing large nearby. If the pulses arrive early and late in repeating patterns, something is tugging. The shape of those timing changes can reveal orbital periods, masses, and the arrangement of the system. It is a little like noticing the presence of a dancer behind a curtain by watching the curtain move. You do not see the dancer directly, you see the rhythm of the disturbance. For PSR B1257+12, that disturbance was not random. That was the key. Space is full of messy effects. Signals pass through the interstellar medium, a thin spread of plasma and dust between the stars. Telescopes have their own limitations. Pulsars themselves can have timing noise, glitches, or other behaviour that complicates the picture. So astronomers must be cautious. They cannot point at a single odd pulse and declare a planet, any more than you should hear one floorboard creak and immediately blame a ghost, although in an old house at night the temptation is understandable. The evidence becomes convincing when the timing variations repeat in the way an orbit should repeat. A planet comes around again and again. Its tug follows a pattern. Over time, the pattern grows clearer. The discovery of this system came from that patient attention. Alexander Volschan and Dale Frail used the Arecibo radio telescope to time the pulsar, and the variations in those timings revealed planet-sized bodies around it. That discovery was surprising not only because these were planets beyond our solar system, but because they were planets around a pulsar. It would have been a major event if they had been found around a sun-like star. Finding them around a stellar remnant made the news feel almost upside down. The universe had taken the first confirmed exoplanetary system and placed it in one of the least gentle settings imaginable. It was as if someone asked nature to show us another version of home, and nature replied, "Certainly, here are worlds orbiting a rapidly spinning corpse of a star." Not exactly the comforting answer, but very informative. There is an important distinction here. The pulse from Lich is regular, but the system is not simple. The planets influence the pulsar, and the planets also influence one another. Poltergeist and Phobator are close enough in their orbital timing that their mutual gravity matters. They are near a 3-to-2 resonance, meaning that their periods have a relationship close to 3 orbits of Poltergeist for 2 of Phobator. Resonances are common in planetary systems. They can help stabilize or shape orbits, and they can reveal the gravitational conversations happening between worlds. In this case, the interactions between Poltergeist and Phobator helped astronomers refine their understanding of their true masses and orbital inclinations. Even around a dead star, the planets are not merely going around in silence. They are tugging, adjusting, and keeping a kind of gravitational conversation, a slow exchange of influence that radio timing can detect. That is one reason the system feels less like a random accident and more like a real planetary architecture. A random scattering of debris would not necessarily produce such orderly, measurable orbits. Poltergeist and Phobator are Earth-mass worlds in stable paths. Draugr is smaller, but it too belongs to the pattern. The system may have formed from a disk of material around the pulsar, possibly after the original star's death, or through a complicated earlier history involving a companion star. We will spend more time with that question later, because it is one of the deepest puzzles in the story. For now, the important point is that Lich is not alone. It is not simply a dead star spinning in isolation. It is the centre of a planetary system, and that makes it both stranger and more revealing. The name Lich also gives us a useful way to think about the system without making it less scientific. The pulsar is not alive, of course, and the planets are not ghosts. But the language helps us sit with the weirdness of a place where ordinary categories feel slightly unprepared. In our own solar system, the sun is the source of life, light, warmth, and stability. Around PSR B1257+12, the central object is the leftover core of a star that has already passed through catastrophe. Around the Sun, planets formed from a disk around a young star. Around Lich, the planets may have formed from debris after death, or survived and rearranged after extreme violence, depending on which formation scenario we consider. Around the Sun, Earth's sky is blue because sunlight scatters through the atmosphere. Around Lich, any sky Poltergeist might have would be shaped by radiation and darkness, by beams sweeping through space, by a star that is less like a lantern and more like a rotating warning signal. If you imagine being somewhere far from the system, looking in from a safe distance, you might not see much at all with ordinary eyes. The pulsar is small, the planets are dark. There is no broad warm glow like sunlight spilling across a family of worlds. Yet in radio waves, Lich announces itself with discipline. Pulse, pulse, pulse. over and over, separated by just milliseconds. The regularity is almost soothing when you think of it from a safe distance, as long as you do not think too hard about what kind of object is making it. It is the steady ticking of something extreme. The universe is very good at pairing calm patterns with violent origins. Ocean waves can come from storms far away. The rings of a tree can record seasons of drought and recovery. And here, a precise pulse comes from the collapsed remnant of a massive star. This is also a reminder that dead stars are not always quiet endings. White dwarfs can cool for billions of years. Neutron stars can spin, flare, accrete, and beam. Black holes can shape whole galaxies through the disks and jets around them. A star's death can leave behind an object that continues to matter for a very long time. Lich is one of those remains. It is not making new elements in a bright core like an ordinary star. It is not shining by fusion. Its energy comes from rotation and magnetic fields, from the leftover motion and structure of an extreme object. Over time, pulsars slow down. Their pulses change, their energy fades. But while they are active, they can be among the most precise natural clocks we know. Natural clocks are rare gifts in astronomy. The universe is large, distant, and not very concerned with making things easy for observers. Stars flicker, gas clouds shift. Gas. Galaxies blur into faint smudges. But pulsars can produce signals so regular that any deviation becomes meaningful. That is why they have been used to test gravity, study interstellar space, search for gravitational waves, and, in this case, find planets. A pulsar is not just an object. It can be a tool, a laboratory, and a clock. And when that clock belongs to a dead star with planets, the timing becomes a map of an invisible system. The ghostly planet family of Lich therefore arrives to us through numbers first, not through landscapes, not through colours, not through weather. Draga, Poltergeist, and Verbitor are known through timing residuals, orbital fits, gravitational perturbations, and careful observations. Those words may sound dry, but they are doing something extraordinary. They are giving shape to worlds we cannot see. A timing residual is just the difference between an expected pulse arrival and an observed one. It sounds small, perhaps even dull, like the sort of phrase that would make a meeting feel longer than it really is. But in this system, those residuals became planets. That is a useful lesson in science. The dramatic discovery is often hidden inside the boring-looking detail. Somewhere in a spreadsheet of pulse arrival times, a planet was waiting, and Poltergeist, true to its name, was not alone in making trouble for the clock. Its neighbouring planets created their own timing signatures. Together they turned the pulsar's pulse into a layered message. The simplest version says, something is orbiting. The better version says, several things are orbiting. The detailed version says, here are their periods, here are their masses, here is how they pull on one another. This is why astronomers can speak about the system with confidence even without images. The pulse carries the information. It arrives at Earth after crossing interstellar space, and in its tiny irregularities it carries the gravitational imprint of planets. There is something gently humbling about that. We often imagine discovery as seeing. We say, I saw it with my own eyes, as if sight is the strongest form of truth. But astronomy repeatedly teaches us that seeing is only one way of knowing. We know black holes by the motion of matter around them, by gravitational waves, by shadows against glowing gas. We know dark matter by its gravity. We know many exoplanets by dips in starlight, or wobbles in stellar spectra. And we know Poltergeist because a dead star's pulse does not arrive quite when it should. The universe does not always hand us pictures. Sometimes it hands us timing problems, and then waits to see whether we are patient enough to solve them. As this picture settles, Lich becomes more than a spooky name. It becomes the centre of one of the most unusual planetary systems ever discovered. A dead star spinning every few milliseconds, a tiny inner world racing around it, a super-Earth named Poltergeist tracing its 66-day orbit, another super-Earth, Phobator, moving farther out. Invisible worlds pulling on an invisible clock, while Earth receives the pulses and slowly turns them into understanding. It is strange, but it is not chaos. It is eerie, but it is ordered. That combination is what makes the system so fascinating. The setting feels like an ending, yet the orbits continue. So for a moment, imagine the pulse again. Not as a sound in your room, but as a signal sweeping through space. It leaves the pulsar, travels outward, passes through thin interstellar material, and eventually reaches a radio telescope on Earth. The telescope records it. Another pulse follows, then another. The timing is compared against expectation. A small shift appears, then another. Over months and years, the pattern grows. What first looks like a flaw becomes a clue. What looks like a restless dead star becomes a planetary system. And once you understand that, the next question begins to form naturally. If the pulse revealed the planets, how did astronomers learn to read it so precisely in the first place? And what did those tiny changes actually look like when the first evidence of poltergeist began to emerge from the timing of a dead star? The story of the discovery begins with a strange kind of listening. Not the listening we do with ears, where a sound enters the room and we turn our head toward it, but the kind done by a radio telescope, patient, silent, and enormous, waiting for signals that have crossed more distance than the human mind can comfortably hold. In the early 1990s, astronomers were not sitting in a control room expecting to find a ghostly little family of planets around a dead star. That would have sounded too odd even for a field that already deals with exploding stars, invisible matter, and galaxies shaped like bent pancakes. They were studying pulsars, and pulsars were already interesting enough. These were crushed stellar remains, spinning rapidly, sending regular radio pulses through space. They were clocks made by catastrophe, and then one of those clocks refused to keep perfect time. PSR B1257+12 had been identified as a millisecond pulsar, meaning that it rotated incredibly fast. Its spin period was about 6.2 milliseconds. That is a difficult number to feel in ordinary life. A blink takes hundreds of milliseconds. A heartbeat takes roughly a second, depending on how calm you are, how much coffee you have had, and whether someone has just said, "We need to talk." This pulsar spun many times in the space of a single blink. Every rotation brought its radio beam across Earth again, so radio telescopes detected pulse after pulse after pulse. If you could slow the signal down enough to imagine it as a ticking clock, it would be almost absurdly fast, like a metronome that had become nervous and then taken up professional sprinting. Yet the important thing was not only that the pulsar was fast, it was regular. A pulsar like this can be timed with extraordinary precision because each pulse can be predicted once astronomers understand the star's rotation. Think of it as a cosmic stopwatch that does not ask for batteries and does not get distracted. Of course, it is not perfect in every possible way. Real pulsars can have complications. Signals travel through interstellar plasma. Earth moves around the sun. The telescope itself sits on a rotating planet. Astronomers must correct for all of that. They have to account for Earth's motion, the position of the pulsar in the sky, the way radio waves are delayed by material between the stars, and the ordinary technical details that come with measuring anything difficult. But after those corrections, the pulses should arrive in an orderly pattern. That is where the clue appeared. The pulses from PSR B1257+12 were arriving slightly early and slightly late, not randomly, not as if the telescope had simply had a bad day, but in a repeating pattern. At first, this might not sound dramatic. A pulse arriving a fraction of a second off schedule does not feel like the opening of a new era in astronomy. It feels more like the sort of error you might ignore if you were checking a microwave clock. But astronomers do not ignore patterns, especially when the pattern keeps coming back. A repeated delay is not just a delay, it is a message. Something was causing the pulsar to move, and that motion was changing the travel time of the pulses on their way to Earth. The basic idea is gentle enough, even though the object involved is not gentle at all. A planet orbiting a star does not simply go around a fixed, unmoving centre. The planet and the star both orbit their shared centre of mass. Because a star is usually much more massive than a planet, the star's motion is much smaller, more like a wobble than a wide orbit. In our own solar system, Jupiter tugs the Sun enough that the Sun shifts around the solar system's centre of mass. We do not usually notice this because we live here, and because the Sun remains very much the large glowing object in charge. But from far away, a careful observer could detect that wobble and infer that planets were present. That method is often used with ordinary stars by looking for changes in the star's spectrum. With PSR B1257+12, the same gravitational principle was read in time itself. When Poltergeist and its neighbouring worlds pulled on Lich, the pulsar moved slightly toward and away from Earth as it responded to their gravity. When the pulsar moved a bit closer, its pulses had a slightly shorter distance to travel, so they arrived a little early. When it moved a bit farther away, the pulses had a slightly longer path, so they arrived a little late. The pulses were still being produced regularly by the spinning neutron star, but the source of the pulses was no longer staying at exactly the same distance from us. The effect was small, but the clock was precise. That combination is what made the discovery possible. If you have a poor clock, small timing errors are just noise. If you have an excellent clock, small timing errors can become a map. A useful way to picture it is to imagine someone standing across a lake with a flashlight, blinking it at you with perfect rhythm. Blink, blink, blink. Now imagine that the person is slowly being carried back and forth on a boat. The blinking rhythm has not changed, but the light has a slightly different distance to cross each time. In real life, light moves so quickly that you would not notice this across a lake, and the person would probably wonder why you are turning a peaceful evening into a physics lesson. But across interstellar distances, and with an object as regular as a pulsar, the same idea becomes powerful. The changing distance leaves a timing signature. That signature can tell you how long the unseen companion takes to orbit and how strongly it tugs. Alexander Fulsjan and Dale Frail recognized that the timing variations in PSR B1257+12 could be explained by planet-sized bodies. This was not an easy claim to make. Astronomy had already seen planet claims come and go, and the field was cautious for good reason. A signal can be misleading. A calculation can contain a hidden mistake. A telescope can show something that later turns out to be caused by an effect no one had properly corrected. Just before this discovery, another proposed pulsar planet around a different pulsar had to be withdrawn because Earth's own motion around the Sun had not been handled correctly in the analysis. So when Wolfsjan and Frail found evidence of planets around PSR B1257+12, the result had to survive careful checking. It was not enough to say, the clock is odd, therefore planet. The timing pattern had to fit orbital motion. It had to repeat. It had to remain after other explanations were removed. That carefulness is part of what makes the discovery so satisfying. The universe did not hand astronomers a bright image of Poltergeist and say, "Here, this is a planet. Please update the textbooks." It gave them pulse arrival times. It gave them numbers, residuals, repeated deviations from a timing model. A timing residual is the difference between when a pulse is expected and when it actually arrives. On its own, the term sounds extremely unromantic. It sounds like something that belongs in a folder on a tired researcher's desk, but in this case, those residuals were the fingerprints of worlds. They were the tiny disturbances made by planets that no human eye could see. The Arecibo Observatory played a central role in this story. Its huge radio dish in Puerto Rico was one of the great instruments of radio astronomy. It could collect faint radio signals from deep space with enough sensitivity for the kind of precise timing work pulsars demand. There is something fitting about the scale of it. To find planets around a dead star, astronomers used a dish so large it seemed less like a tool and more like a landscape. Arecibo sat in a natural limestone sinkhole, fixed into the ground, listening upward. It was not slewing around the sky like a small backyard telescope. It was an immense ear pressed gently against the radio universe, and through it came the pulses of PSR B1257+12. The discovery unfolded through repetition. One observation would never have been enough. A pulsar needs to be timed again and again, over days, months, and years. Each pulse arrival adds another point to the record. The longer the record, the clearer slow patterns become. If a planet takes about 66.5 days to orbit, as Poltergeist does, astronomers need enough time to see the cycle repeat. They need to separate it from other cycles, other possible causes, and the motion of Earth itself. It is patient work, and patience is not always the glamorous side of science, but it is often the side that finds things. The universe is under no obligation to reveal itself in a single dramatic moment. Sometimes it reveals itself by being slightly wrong in the same way over and over. Once the timing variations were modelled, they pointed to more than one companion. That was one of the extraordinary parts. The pulsar was not simply being tugged by one object. The pattern suggested a small system. At first, the two larger planets were identified, the worlds we now know by the names Poltergeist and Phobator. Later, the smaller inner planet Draugr was confirmed. The names came later too, but the architecture was already there in the timing. Two substantial Earth-mass planets, and then a tiny inner world, all orbiting a pulsar that had no business being a comfortable home for planets by ordinary expectations. It was as if astronomers had opened what they thought was a clock and found a miniature solar system hidden inside. Poltergeist's signal came from its gravity, not from its light. That matters because many exoplanets are found by watching starlight change. In the transit method, a planet passes in front of its star and blocks a tiny fraction of the light, producing a dip. In the radial velocity method, a planet's gravity makes a star wobble, shifting its spectral lines. Those methods depend on ordinary starlight in one way or another. Pulsar timing is different. It depends on the pulses. That means it can detect very small planets if they orbit a highly stable pulsar, because even a modest gravitational tug can cause measurable timing changes. In some ways, pulsar timing is one of the most precise planet hunting techniques ever used. The difficulty is that pulsars are rare, extreme, and not especially likely to host planets. It is a remarkable method, but not a method you can apply to every calm star in the sky. This also explains why the discovery was so surprising. If you were designing a search for planets in the most sensible way, you might look around stars like the Sun, or perhaps around smaller red dwarfs, which are very common. You might expect planet formation to occur in disks around young stars, where dust and gas can gather gradually. A pulsar seems like the aftermath of planetary destruction. The supernova that creates a neutron star is violent enough to tear apart or eject nearby planets. So a planetary system around PSR B1257+12 raised immediate questions. Had these planets somehow survived? Had they formed later from debris? Were they the remains of a companion star that had been disrupted? The discovery did not just add planets to a catalogue, it opened a problem. In that sense, Poltergeist was not only a world, it was evidence that planets could exist in places that seemed almost unreasonable. That is why it mattered so much to the wider search for exoplanets. Today, the discovery of a new exoplanet is exciting, but it enters a field already filled with thousands of known worlds. In 1992, the situation was very different. Astronomers had long suspected that planets existed around other stars, because it would have been strange for the solar system to be unique, but firm detections were hard. Poltergeist and Phobator helped show that other planetary systems were real. The twist was that the first confirmed examples came from a dead star. It was a bit like proving that gardens exist elsewhere by finding flowers growing in the ruins of a chimney. There is another subtle point here. Pulsar timing did not only detect the planets, it allowed astronomers to test the system in ways that strengthened the case. Poltergeist and Phobator are close enough in their orbital periods that they gravitationally perturb each other. Their orbits are near a 3:2 resonance, which means their motions line up in a repeating relationship. This mutual interaction created additional timing effects. Those effects were not just an inconvenience, they were useful. They helped confirm that the objects were real planets interacting with one another, not just unrelated timing noise. If two unseen worlds tug on each other, and the pulsar's pulse records the result, then the system begins to behave like a set of connected gears. The pattern becomes harder to dismiss as a mistake. This is one of the loveliest pieces of the discovery, if we can use a gentle word for something so technical. The planets confirmed one another through gravity. Poltergeist tugged the pulsar. Phobator tugged the pulsar. They also tugged each other. The timing record carried all of this in small deviations measured over time. It is like hearing three musicians in another room, not by hearing their instruments directly, but by noticing how the floorboards vibrate when they play together. One vibration might be confusing. A repeated rhythm is clearer. A rhythm that changes because the musicians are responding to one another is clearer still. Around Lich, the planets were not seen, but their gravitational pattern had structure. Of course, the discovery also required mathematical modelling. The raw data did not arrive with labels. No pulse came stamped with the message, "This one is late because of Poltergeist." Astronomers had to build models of what the pulsar's timing should look like if planets were present. They had to fit orbital periods, masses, eccentricities, and other parameters. The orbit of Poltergeist turned out to be nearly circular, with a period of about 66.5 days and a mass several times that of Earth. These details came from the shape and size of the timing variations. A more massive planet causes a larger wobble. A farther or closer planet changes the timing pattern differently. The orbital period shows up in the repeating cycle. With enough data, the invisible begins to take on form. There is a quiet discipline in this. Science often advances by refusing to be satisfied with a dramatic idea until the numbers behave. A planet around a pulsar sounds wonderful in the way strange ideas can sound wonderful. But sounding wonderful is not the same as being true. The timing had to match. The alternative explanations had to fail. The observations had to continue. This is why the discovery became strong. It was not a single flash of inspiration floating unsupported. It was a pattern measured by an instrument, analysed through physics, and confirmed by continued observation. The ghost had footprints. If we stay with the name Poltergeist for a moment, the timing method makes it feel especially appropriate. In stories, a poltergeist is not usually seen directly. It is inferred from disturbances. A cup moves, a wall knocks, a door opens when nobody is there. The whole point is the unseen cause. Poltergeist the planet behaves in a much more respectable way, thankfully, and has not thrown any cups that we know of. But it too was inferred from disturbances. It moved the pulsar by gravity. The pulsar's movement shifted the pulse arrival times. The timing record knocked gently on the door of the model until astronomers opened it and found a planet standing there, metaphorically speaking, because opening a door in interstellar space is not recommended. What makes this even more remarkable is that Poltergeist was not found by accident in the shallow sense. It was unexpected, yes, but the discovery came because astronomers were already paying close attention to an object most people would never think about at all. Pulsar timing is a specialized practice. It requires understanding the pulsar, the telescope, Earth's motion, radio propagation, and the mathematics of orbital motion. It is easy to look back and say, the planets were in the data, but that is true of many discoveries before they are made. The challenge is knowing how to recognize them. The pulse had to be treated as a clock. The clock had to be trusted enough that its tiny irregularities became suspicious. Then those irregularities had to be explained by something physical. This is one of the reasons the discovery still feels important decades later. It demonstrates a very particular kind of astronomical reasoning. We do not need to visit a place to know something about it. We do not need to photograph a planet to detect its mass. We do not need sunlight to reveal an orbit. We can use timing, gravity, and patience. That is a powerful combination. It turns a dead star into an instrument and a planet into a timing error with a name. For listeners here on Earth, it may also be comforting in a strange way to remember that discoveries like this are not made because the universe is close or easy. They are made because patterns survive the distance. A pulse leaves Lich. It travels for hundreds or thousands of years, depending on the distance estimate being used. It crosses space that is thin but not empty, passing through clouds of charged particles in the wide dark between stars. It reaches a radio telescope built by humans on a rotating planet. The signal is recorded, corrected, compared, and interpreted. From that chain comes the knowledge that Poltergeist exists. The connection is fragile in one sense, because it depends on careful measurement, but strong in another, because gravity and light follow rules across enormous distances. The discovery also changed the emotional shape of the exoplanet search. Before thousands of confirmed exoplanets, before space telescopes routinely found dips in starlight, before catalogues filled with strange worlds, these pulsar planets offered a first clear proof that planets were not limited to our solar system. But they did not offer a comforting twin of Earth. They offered a warning that the universe's imagination is wider than ours. The first confirmed worlds were not orbiting a star like the Sun. They were circling a dead star named Lich. One of them, Poltergeist, was a super-Earth in a tight orbit, detected by the slight delay in advance of pulses from a neutron star. If that sounds like science fiction, it is only because science fiction has often borrowed from the real universe, and the real universe is rarely modest about its ideas. As the timing record improved, the planets became less like hints and more like measured bodies. Poltergeist had an orbit, it had a mass, it had neighbours, it belonged to a system. That transformation, from suspicion to measurement, is one of the great quiet pleasures of astronomy. A faint irregularity becomes an object becomes a world becomes part of a larger story about how planets form, survive, or are rebuilt after disaster. The discovery method tells us where the story begins, but not where it ends. It tells us that Poltergeist is there, circling the pulsar with a year shorter than one of our seasons. It tells us that its gravity speaks through time. It does not yet tell us what the planet is made of in detail, what its surface might be like, or whether it formed from the wreckage of the star's death. Once we know how Poltergeist was discovered, the next question becomes almost unavoidable. What kind of world is it? Not just where is it? Not just how fast does it orbit? Not just how does it tug on a dead star's pulse? But what is this thing actually made of? That sounds like a simple question at first, the sort of question you might ask about a stone picked up from a beach, or a strange object found at the back of a drawer. Is it rock, metal, ice, something else entirely? But with Poltergeist, the answer has to be approached carefully, because this is not a planet we can see directly. We do not have a photograph of its surface. We do not have a spectrum of its atmosphere. We have not watched it pass in front of its star and measured the way starlight filters through its air, because its star is not a normal shining star, and the discovery did not happen that way. Poltergeist is known mostly through gravity and timing. We know it is there because it pulls. We know its mass because of how strongly it helps disturb the pulsar's pulse. But knowing mass is not the same as knowing composition. A planet can weigh a certain amount and still have more than one possible inner story. Poltergeist is usually called a super-Earth, and that term can be a little misleading if we let it sound too friendly. A super-Earth is not necessarily Earth, but nicer, like an upgraded hotel room with better towels. It simply means a planet more massive than Earth, but much less massive than giant planets like Neptune or Jupiter. Some super-Earths may be rocky, some may have thick atmospheres, some may be water-rich. Some may be stripped cores or compressed worlds with interiors unlike anything in our solar system. The name tells us the planet's size or mass category, not whether it has oceans, continents, mild weather, or anywhere pleasant to sit with a cup of tea. In Poltergeist's case, we know its mass is about 4.3 times the mass of Earth, and it orbits its pulsar at about 0.36 astronomical units, completing 1 year in about 66.5 Earth days. Those numbers tell us it is substantial, not a tiny asteroid, not a gas giant, but a real planet-sized body. What they do not tell us directly is whether its deep interior is mostly silicate rock, iron, carbon-rich material, or something reassembled from the leftovers of a dead star's complicated past. Still, we're not completely helpless. Astronomy often works by narrowing the possibilities rather than opening a box and looking inside. If a planet has a few times Earth's mass and is part of a compact system of low-mass planets, a rocky or terrestrial-like composition is a reasonable starting point. That does not mean Earth-like in comfort. It means made mostly of heavier materials, the kinds of substances that can build solid planets, rather than vast envelopes of hydrogen and helium. Around an ordinary young star, rocky planets form from dust grains made of minerals, metals, and other solid compounds. These grains collide, stick, break, stick again, grow into pebbles, then boulders, then planetesimals, then planetary embryos. Eventually, with enough time and enough collisions, something like a terrestrial planet can emerge. Around Lich, the story cannot be that simple, because the central star is not young and gentle. It is a neutron star, the remnant of a supernova. So if Poltergeist is rocky, the material had to either survive a stellar catastrophe or gather afterward from debris. Neither option feels casual. The phrase "in the ashes" is useful here because it points to the great mystery of the planet's origin. A supernova does not politely step around planets. When a massive star explodes, it throws its outer layers into space at enormous speeds. Radiation floods the surroundings. Orbits can be disrupted. Existing planets can be stripped, shattered, or ejected. If any original planets existed around the massive star before it died, they would have faced conditions far beyond the usual hazards of space. A normal planet might survive at a great distance, perhaps, but the compact inner system we see around PSR B1257+12 is harder to explain as a simple group of survivors. The planets are close, their orbits are orderly. Poltergeist and Phobator are near a gravitational relationship that suggests a shared formation history. That has led many researchers to favour some kind of disk origin, where material formed a disk around the pulsar and planets assembled from it later. In other words, Poltergeist may not be a survivor of the star's original youth. It may be a second-generation world built after death. That idea is strange, but not unreasonable. The universe makes disks very easily whenever material has angular momentum and a central object to orbit. Young stars have protoplanetary disks. Black holes can have accretion disks. White dwarfs can have debris disks from torn-apart asteroids. Even a pulsar, under the right circumstances, might be surrounded by material that settles into a flattened, rotating structure. Where would the material come from? There are several possibilities. Some could be fallback material from the supernova, matter blasted outward, but not quite fast enough to escape forever, falling back toward the compact remnant and forming a disk. Another possibility involves a companion star that once fed material onto the neutron star, spinning it up into a millisecond pulsar and leaving behind a disk from which planets could form. There are also scenarios involving the destruction or disruption of a companion, with its remains becoming raw material for new worlds. These are not tidy stories, but the system itself is not tidy in its origin. It is tidy now in its orbital structure, but its past may have been a mess of collapse, transfer, debris, and rebuilding. If Poltergeist formed from a disk after the pulsar was already present, then its composition would depend on the nature of that disk. A fallback disk from a supernova could be rich in heavy elements, because supernova ejecta contains material processed inside the star. A disk from a disrupted companion might have a different mixture, perhaps more like the outer layers of a star or the remains of a stripped object. A disk that had time to cool and allowed dust to settle could form solid bodies. The details matter because planets are recipes, and the ingredients decide what kind of world emerges. More iron gives a larger metallic core. More silicates give a rocky mantle. More volatile material, if it can survive, can provide ices or gases. Around a pulsar, however, volatile materials face a difficult life. Intense radiation and particle winds can erode atmospheres and strip lighter substances away. If Poltergeist began with a thick envelope of gas, it may not have kept it. If it once had surface volatiles, they may have been altered or removed. A pulsar is not gentle with delicate materials. This is one reason Poltergeist is often imagined as a hard world, probably rocky or metallic, perhaps with an iron-rich interior and a silicate crust or mantle. But we have to keep the word probably nearby like a small safety rail. We do not know its radius from a direct transit measurement in the same way we know the radii of many planets found by space telescopes. NASA's catalogue gives an estimated radius, but an estimate is not the same as a measured planetary disk crossing a star. Without a reliable radius and mass together, we cannot calculate density in the usual helpful way. Density is what often lets astronomers distinguish a rocky planet from a gas-rich or water-rich one. If you know a planet's mass and radius, you can ask whether it is compact like rock and metal, puffier like a mini Neptune, or somewhere in between. For Poltergeist, the pulsar timing gives excellent mass information, but the rest is more indirect. So the honest answer is that Poltergeist may be a rocky super-Earth, but we do not have a sample, a surface image, or a direct density measurement that lets us speak with the confidence we might like. Even so, a mini Neptune-like world would be difficult to maintain around a pulsar over long times. Large envelopes of hydrogen and helium are vulnerable to intense high-energy radiation, especially close to a compact energetic object. Around ordinary stars, close-in planets can lose atmospheres through photoevaporation. Around a pulsar, the environment can be even harsher, because the object sends out high-energy particles and radiation from its magnetic activity. That does not automatically erase every atmosphere in every case, but it makes a thick, light gas envelope less likely to survive for billions of years on a close-in world. A more compact planet made of heavier material seems more plausible. If Poltergeist has an atmosphere at all, it may be thin, unusual, temporary, or constantly altered. It may also have no meaningful atmosphere in the way Earth does. It might be exposed rock and metal under a sky dominated not by sunlight, but by the sweep of radiation from the pulsar. That is not a bedtime resort, unless your bedtime routine includes being sandblasted by charged particles, which I hope it does not. The name Super-Earth also invites a comparison with our own planet, so let us make the comparison carefully. Earth has a layered interior, an iron-rich core, a rocky mantle, a crust, water at the surface, and an atmosphere held by gravity and maintained by geological and biological processes. Poltergeist, if rocky, may also have layers. A planet with several Earth masses can become hot inside from its formation, from radioactive decay, and from compression. Its gravity would be stronger than Earth's if its radius is not too much larger. The pressure deep inside would be enormous. Its mantle could behave differently. Its core might be proportionally larger or smaller depending on its formation material. If it formed from heavy element-rich debris, perhaps it could be more metal-rich than Earth. If it formed from a more solar-like disk after dust sedimentation, perhaps it could resemble a scaled-up terrestrial planet. These are possibilities, not certainties. We are looking at Poltergeist through the indirect window of orbital dynamics, and the window is clear for mass but frosted for geology. What about carbon? It is tempting, with a strange planet around a dead star, to imagine something exotic, maybe a carbon planet, maybe diamond layers, maybe a world made of materials that sound as if they belong in a jewellery shop run by a neutron star. Carbon-rich planets are a real theoretical idea, and some unusual exoplanet environments may encourage chemistries very different from Earth's. But for Poltergeist specifically, we do not have evidence that it is a diamond planet or a carbon planet. It may contain carbon, as most planetary material can, but that is different from saying carbon dominates its composition. This distinction matters because space already gives us enough real strangeness without needing to decorate it too much. A rocky super-Earth built in the debris of a dead star is already extraordinary. It does not need a gemstone interior to be interesting, although if the universe later provides evidence for one, we will of course update the mental furniture. The more grounded strangeness lies in how its material may have been processed. If Poltergeist formed after the supernova, then some of its ingredients may have passed through a violent stellar death. Heavy elements forged in stars, scattered in explosions and gathered again into planets, are the normal story of cosmic recycling. But here that recycling may have happened in an especially direct and compressed way. Our own Earth is made from elements created in earlier generations of stars. Iron, silicon, oxygen, magnesium, nickel, carbon, calcium, all of these came from cosmic processes older than the solar system. Earth is already a child of stellar ashes in the broad sense. Poltergeist may be a child of ashes in a more immediate sense, assembled near the remnant of the very catastrophe that helped provide its material. That gives the phrase a sharper edge. It is not only poetic language, it may be close to the system's physical history. A planet forming in a post-supernova or post-interaction disk would have faced unusual conditions. The disk might have been compact, hot, and rapidly evolving. Dust grains would need to form or survive, settle toward the mid-plane, and build larger bodies. Radiation from the pulsar could influence the disk's chemistry and structure. The available material might be limited compared with the original disk around a young star, so the planets could form close together. This may help explain why the known planets of Lich occupy relatively compact orbits. Poltergeist and Phobitor are not scattered across a vast planetary system like Jupiter and Saturn. They sit close enough that their mutual gravitational influence is measurable in the timing of the pulsar. Their masses, orbital relationship, and near coplanar arrangement all fit the idea that they formed from a disk rather than being random captured bodies. Capture is possible in some astronomical settings, but capturing several low-mass planets into neat orbits around a pulsar is not the easiest explanation. The system looks assembled, not merely collected. If Poltergeist is rocky, what might its surface be like? Here, we must step from knowledge into informed imagination. A super-Earth with no thick atmosphere might have a cratered, dark, radiation-battered surface. Without weather like ours, features could persist for long periods, unless volcanic or tectonic activity reshapes them. If the planet has internal heat, it could have geological activity, especially because a larger rocky planet may retain heat longer than Earth. But its exact tectonics would depend on composition, internal temperature, water content, crust strength, and many things we do not know. Plate tectonics, for instance, is not guaranteed on rocky planets. Venus and Mars are rocky worlds too, and neither operates like Earth today. Poltergeist could have a stagnant lid, a thick crust, or some different mode of heat release. It might be geologically dead, or it might have once been active, or it might still have internal processes hidden beneath a harsh exterior. We simply cannot say for sure. Surface temperature is also not straightforward. With an ordinary star, we could estimate energy from starlight and think about equilibrium temperature. Around a pulsar, heating can come from high-energy radiation and particle bombardment rather than ordinary visible light. A planet's temperature would depend on how much of that energy reaches and is absorbed by the surface or atmosphere, how the planet rotates, whether it has any atmosphere to move heat around, and how much internal heat it retains. It may be cold in the ordinary thermal sense while still being exposed to dangerous radiation. This is a useful distinction. A place can be dark and cold but still hostile. Space does not need warmth to be dangerous. A pulsar can make an environment chemically and biologically severe even if it does not provide a sunny afternoon. Could there be ice? Perhaps some heavy volatiles could exist in protected places or beneath the surface, but close to a pulsar and after such a violent history, it is hard to imagine Poltergeist as an icy ocean world in the familiar sense. If it formed from debris poor and volatiles, it may have been dry from the start. If it once had volatile material, radiation could have removed or transformed much of it. Subsurface reservoirs are harder to rule out because rock can protect material from radiation and planets can hide things well. Earth itself hides oceans of minerals, fluids and heat beneath its surface, but again, with Poltergeist, we have no direct evidence for water, ice or an atmosphere. The most cautious picture is a massive terrestrial-type planet, likely dominated by rock and metal, shaped by a formation story unlike Earth's, and by an environment much harsher than anything in our solar system's comfortable middle regions. The word ashes also makes us think of a burned remnant, something grey and finished. But in astrophysics, ashes are often ingredients. The ashes of stars are not useless. They are the raw material of everything solid. The calcium in bones, the iron in blood, the silicon in rocks, the oxygen in water, all of it belongs to a long chain of stellar processing. Poltergeist reminds us of this in a more dramatic setting. If its material came from a disk around a neutron star, then the planet is an example of matter reorganizing after disaster. The original star died, but its death did not produce only emptiness. Some material remained or returned or was supplied later. Gravity gathered it. Collisions built it. Time allowed it to settle into an orbiting world. That does not make the place gentle, but it does make it meaningful. It shows that planet formation can be stubborn. Given material and a disk, nature often begins building. There is also a difference between being made from ashes and being fragile. Poltergeist is not a ghost in the sense of being insubstantial. It is several times Earth's mass. Its gravity is real. It pulls on a neutron star enough for us to detect the effect across interstellar distance. That is not a small achievement for a world we cannot see. Its name suggests something eerie and invisible, but its physical presence is strong. It is not just a trace, it is a planet with enough mass to participate in a measurable gravitational arrangement with its neighbours. In a way, Poltergeist is both hidden and powerful. It does not shine for us, but it moves the clock. Thinking about its composition also changes how we think about planet as a category. We often picture planets as belonging to a star's life, forming in youth and aging alongside it. Poltergeist complicates that picture. It may be a planet of a second act, a world that belongs not to the star's bright main life, but to its aftermath. If it is rocky, then rock can gather after a supernova. If it is metal-rich, then heavy elements can settle into a world around a dead core. If its surface is stripped and bare, then a planet can still be a planet without comfort, without air, without sunlight. A planet is not defined by being habitable or familiar. It is defined by its mass, its orbit, its formation, its physical reality. Poltergeist is a planet even if no ocean ever touched it, even if no sunrise ever warmed it, even if its sky is ruled by beams from a dead star. This is a useful point because exoplanet science has taught us again and again that the universe does not build planets only to resemble Earth. Earth is one outcome. A beautiful one from our biased and breathing point of view, but not the template for everything. There are hot Jupiters skimming close to their stars, lava worlds with molten surfaces, mini Neptunes wrapped in deep atmospheres, circumbinary planets orbiting two stars, rogue planets drifting without any star at all, and pulsar planets like Poltergeist moving around stellar remnants. Each one expands the meaning of the word. Poltergeist expands it in a particularly stark direction. It says that a planet can be born or rebuilt beside a neutron star. It says that even after a star dies, orbital order can remain or reappear. If we imagine Poltergeist as a solid world, perhaps its interior is a compressed arrangement of iron and silicate, with a core heavier than Earth's, a mantle under greater pressure, and a surface long altered by impacts and radiation. Perhaps its crust contains minerals formed under conditions uncommon on Earth. Perhaps the material in its body carries isotopic signatures of supernova processing, if only we could sample it. Perhaps it has no atmosphere, or perhaps it has a thin envelope sputtered from its surface, constantly lost and replenished in small ways. Perhaps the side facing the pulsar, if it is tidally influenced in some way, experiences different radiation exposure than the far side, though its rotation state is not something we can simply assume. These possibilities are not decorations for certainty. They are the careful edges of what might be true, built around the few things we know. What we know is enough to make the planet remarkable. A mass around 4.3 Earths, a close orbit around a millisecond pulsar, a place in a compact system with other low-mass planets, discovery through timing, evidence from the system structure that a disk origin is plausible. Everything beyond that must be held gently. There is a special kind of honesty in saying, we do not know what its rocks look like. It does not weaken the story. It makes the story more real. Science is not only the list of things already known, it is also the boundary where the known fades into the possible. Poltergeist sits very comfortably on that boundary, or perhaps uncomfortably given the radiation. So, when we ask what Poltergeist may be made of, the best answer is not one material but a history. It may be made of rock and metal, like a large terrestrial planet. It may contain material processed by a supernova or gathered from a disk formed after violent stellar evolution. It may have lost lighter gases long ago under the pulsar's harsh radiation. It may be a solid world assembled from debris where no gentle planet should have been expected. It is not Earth's twin. It is not a friendly super-Earth waiting under a yellow sun. It is a heavy hidden world in the aftermath of stellar death, a planet whose body may be built from the remains of catastrophe, and whose presence is known because it tugs on a dead star's timing, and once that physical picture begins to take shape, the system becomes even stranger. A super-Earth of rock and metal is already impressive. A super-Earth rebuilt from ashes is stranger still. But now we have to place that world back into its environment. Not just what it is made of, but what it means to orbit a pulsar. What kind of sky does a planet have when its star is a spinning neutron core? What replaces sunlight when the central object is a lighthouse of radiation? What happens to a world when its days and years are measured not beneath a warm star, but beside the flashing remnant of one that died long ago? To understand Poltergeist, we have to stop thinking of a star as a lamp. That is natural for us, because our own star behaves like one from the surface of Earth. The sun rises, fills the sky with daylight, warms the ground, grows plants, drives weather, and gives the planets around it a familiar sense of order. It is dangerous up close, certainly, but at Earth's distance it is the reason the world feels alive rather than frozen. Around a pulsar, that simple picture breaks. A pulsar is not a friendly glowing sphere giving steady visible light to its worlds. It is the collapsed core of a dead star, a neutron star with a powerful magnetic field, spinning rapidly and sending beams of radiation through space. So to orbit a pulsar is not just to go around a smaller, stranger sun. It is to live beside a cosmic machine left behind by an explosion, a lighthouse made from a stellar corpse, where the idea of daylight has been replaced by pulses, particle winds, and high-energy radiation. Poltergeist moves around PSR B1257+12 at a distance of about 0.36 astronomical units, which is roughly a little more than a third of Earth's distance from the Sun. If you heard only that number and forgot what it was orbiting, you might imagine a warm world. In our solar system, an object that close to the Sun would sit inside the orbit of Mercury. it would be baked by sunlight. But Lich is not the sun. It is not shining by nuclear fusion in a broad golden photosphere. It is a small, dense remnant, perhaps only about the size of a city, with more mass than the sun packed into it. Its energy does not arrive as gentle sunshine spread over a round, stellar surface. It comes through rotation, magnetism, and radiation. It is the difference between sitting near a fireplace and sitting near a spinning emergency beacon attached to a power plant that used to be a star. The first strange thing about orbiting a pulsar is that the central object is tiny. Not low in mass, but tiny in size. The sun is enormous compared with Earth, wide enough that more than 1 million Earths could fit inside it by volume. A neutron star is only tens of kilometers across. From the surface of a nearby planet, if you could somehow stand there safely and look up with protected eyes, the pulsar might not look like a broad disk in the sky. It could appear more like an intensely compact point, not a warm circle, but a sharp source of danger. That small apparent size changes the feeling of the system. There is no big sun filling the day. There is no gentle golden arc rising over the horizon. There is a dark sky ruled by a tiny remnant, whose true power is not in its visible size, but in its density, magnetism, and speed. The second strange thing is the pulse. A pulsar emits beams from regions around its magnetic poles. Because the magnetic axis is not always aligned with the rotation axis, those beams sweep around as the star spins. When one crosses Earth, we detect a pulse. For a planet in the system, the experience would depend on its orbit, its orientation, and whether those beams sweep across it. If the beam crossed Poltergeist, the planet could be struck repeatedly by bursts of radiation with the rhythm of the pulsar's spin. PSR B1257+12 is a millisecond pulsar, spinning in just a few thousandths of a second. That means the pulses are not occasional lighthouse flashes separated by long, calm intervals. They are rapid, relentless, a rhythm far too fast for human senses to follow one by one. If somehow converted into sound, it would not be a slow heartbeat. It would be a sharp buzz, a frantic ticking, a dead star keeping time with terrifying discipline. But even that image needs care. A planet does not simply sit there listening to radio pulses as if they were harmless beeps. Pulsars can produce radio waves, X-rays, gamma rays, and streams of energetic particles. The environment around them can be harsh in ways that do not match ordinary sunlight. On Earth, sunlight can burn skin, damage eyes, and drive atmospheric chemistry, but our magnetic field and atmosphere protect life from much of the sun's more dangerous behaviour. Poltergeist would not have that same easy protection. If it has an atmosphere, the pulsar's radiation and particle wind could erode it, heat it, strip it, or chemically alter it. If it has no atmosphere, the surface would be exposed more directly to radiation. Either way, the planet's relationship with its star is not a gentle exchange of light and warmth. It is a long encounter with a compact engine. A pulsar wind is another piece of the story. Pulsars can release streams of charged particles moving outward through their magnetospheres and into space. These particles carry energy away from the spinning neutron star. Around some pulsars, this creates glowing nebulae, where particles slam into surrounding material and produce spectacular structures. PSR B1257+12 is not the Crab pulsar, and we should not borrow another pulsar's drama too casually, but the basic idea remains important. A pulsar is not only a flashing point, it can fill its surroundings with energetic particles and electromagnetic influence. For a planet orbiting close by, that means the space environment is active. It is not empty darkness with a small dead star sitting quietly in the middle. It is a region shaped by magnetic fields, radiation, and charged particles, all flowing from a remnant that is slowly losing rotational energy. That has consequences for habitability, or more honestly, for the lack of it. Around normal stars, astronomers often talk about the habitable zone. the region where a rocky planet could have liquid water on its surface if it has the right atmosphere. The phrase is useful but often misunderstood. It does not mean every planet in that zone is habitable, only that the amount of starlight could allow surface water under the right conditions. Around a pulsar, the usual habitable zone idea becomes much less helpful. The energy is not sunlight in the ordinary sense. It is high-energy radiation and particles that can destroy or strip atmospheres. A planet might be at a distance where the total energy input seems interesting on paper, but the form of that energy matters. A warm rain and a shower of high-energy particles are not the same thing, even if both involve things arriving from above. So if Poltergeist has a surface, it is probably not a place of calm sunrise and sunset. It may be dark much of the time in visible light. Any illumination from the pulsar might be faint to human eyes, unless there is reprocessed light from surrounding material or radiation interacting with an atmosphere or surface. The sky could be mostly black, with the compact pulsar as a strange point source, perhaps accompanied by flashes or auroral effects if the planet has magnetic fields or gases for particles to excite. If Poltergeist has no significant atmosphere, then there may be no blue sky, no clouds, no weather as we know it. Just hard ground under a black sky, with radiation passing through or striking the surface. If there is a thin atmosphere, it might glow, sputter, escape, or behave in ways controlled by the pulsar's energy, rather than by ordinary daylight cycles. The orbit itself is also different from our emotional idea of a year. Poltergeist completes one trip around Lich in about 66.5 Earth days. That means its year is shorter than a season on Earth. If it had seasons, which would depend on its axial tilt and atmosphere and other unknowns, they would move quickly by our standards. But the main rhythm of the planet may not be the year at all. Around a pulsar, the dominant external rhythm might be the pulse. The dead star spins many times per second. The year is slow compared with that. The orbit carries the planet around in weeks, while the pulsar flashes in milliseconds. This gives the system a strange layering of time, the frantic spin of the neutron star, the steady orbit of the planet, the longer gravitational interactions with neighbouring worlds, and the slow fading of the pulsar over astronomical ages. Gravity near the pulsar is also an interesting question. Poltergeist orbits at a safe distance in the sense that it is not skimming just above the neutron star's surface. At 0.36 astronomical units, it is far from the strongest near-surface gravity. You would not feel the neutron star's crushing gravity directly the way you would if you were foolish enough to approach the surface, which, to be clear, is not a recommended field trip. The planet is in orbit, falling around the pulsar just as Earth falls around the Sun. From the planet's surface, the local gravity would mostly come from the planet itself. If Poltergeist is a rocky super-Earth, surface gravity could be stronger than Earth's, depending on its radius. A person standing there, ignoring all the reasons they could not survive, might feel heavier. But the pulsar's gravity would govern the orbit, not pin you flat to the ground from far away. This is one of those details where space is strange, but still obedient to the rules. The more extreme danger comes from the pulsar's radiation and its history. The star that became Lich likely exploded as a supernova, long before the current planetary system settled into the form we observe. That explosion either destroyed an earlier arrangement or provided the conditions for a later one. Now the planets orbit the remnant. It is as if they are circling the afterimage of disaster. The central object is small and dark in visible light, but it carries the legacy of a star's death. To orbit a pulsar is to orbit a memory that still has teeth. The original star is gone, but its core remains, and that core is still capable of shaping everything nearby. For Poltergeist, the closeness of its orbit means it is deep inside the system's gravitational architecture. It is not a far-off body drifting lazily in the outskirts. It is one of the larger known planets close to the pulsar, and it participates in the timing pattern that revealed the system. Its orbit is also close enough to Phobotors but the two planets gravitationally disturb each other in measurable ways. That is important because it tells us that Poltergeist is not simply a lonely rock around a dead star. It is part of a compact family. The planets are locked into a shared dynamical environment, tugging on the pulsar and on one another. Their motions have to remain stable over long periods, otherwise we would not see the system as it is today. In a place born from violence, the current orbits are surprisingly orderly. That order should not be overlooked. It is easy to focus on the eerie parts of the system, the dead star, the ghostly names, the radiation, the ash. But orbiting a pulsar also means participating in one of gravity's most patient habits. Gravity builds patterns. Even in extreme systems, it can produce regular paths, resonances, and long-term stability. Poltergeist circles Lich again and again. Its neighbour Phobator circles farther out. Tiny Draugr moves closer in. The planets do not need warm sunlight to keep orbiting. They do not need comfort to obey gravity. They continue because motion and gravity have arranged them into a working system. There is something almost calming about that. The environment is harsh, but the orbit is steady. Still, if we imagine the view from Poltergeist, steady does not mean safe. The pulsar's beam, if it crosses the planet, would sweep over it with extreme regularity. The radiation could interact with the surface, breaking molecules apart, charging dust, altering minerals, and stripping any exposed atmosphere. On Earth, our atmosphere protects us from many incoming particles and rays. It also turns sunlight into a familiar environment of scattered blue light, warmth, weather, and sound. Without an atmosphere, a planet has no soft boundary between ground and space. The sky is not a dome. It is just the universe beginning immediately above you. Around a pulsar, that immediate universe would be filled with a kind of invisible weather made of radiation and charged particles. Could Poltergeist have a magnetic field of its own? We do not know. Earth's magnetic field helps shield us from the solar wind, though the atmosphere also plays a major role in protecting life. A super-Earth might have a magnetic field if it has a convecting metallic core and the right rotation and internal conditions. But having a magnetic field near a pulsar could be a complicated blessing. It might deflect some charged particles, channel others toward magnetic poles, and create intense auroras if an atmosphere is present. The interaction between a planet's magnetosphere and a pulsar wind could be dramatic, but without direct observations, this remains a field of cautious imagination. We can say the environment gives magnetic shielding a very difficult job. Whether Poltergeist has such shielding is unknown. Tidal effects are another piece people sometimes wonder about. A planet close to its star can become tidally locked, always showing the same face, as the Moon does to Earth. But tidal locking depends on the masses involved, the distance, the planet's internal structure, and the age of the system. A neutron star is massive, so tides can matter, but Poltergeist's distance is not extremely tiny in the way some hot Jupiter's distances are. We cannot simply assume its rotation state without evidence. It may rotate in a way shaped by tides, past collisions, or formation history. If it were tidally influenced, one side might have a different radiation exposure pattern depending on its orientation and the pulsar beam geometry. But again, we should not decorate the unknown too firmly. The honest picture is that Poltergeist's day, if we can call it that, is not measured for us. We know the year. The day remains hidden. The idea of day and night around a pulsar is itself a little slippery. On Earth, day and night are defined by the sun's position in our sky. The planet rotates, sunlight comes and goes, and life has built rhythms around that cycle. Around Lich, visible light may be weak, and the radiation beams may not behave like broad daylight. If the beam strikes the planet, it might create pulses of energy rather than a stable daytime. If it misses the planet, then the planet may receive other forms of radiation and particles without that direct lighthouse sweep. If the pulsar is seen as a point source, then ordinary shadows would be different from Earth's. A rock on the surface might cast a sharp shadow under point-like illumination, if there is enough visible light to matter. But the more important energy may be invisible to human eyes, so day and night may not be the main story. Exposure and shielding may matter more. There is also the question of sound, which is always tempting in a place described through pulses. On Poltergeist, if there is no atmosphere, there would be no sound at the surface, no roar from the pulsar, no audible ticking, no wind carrying the dead star's rhythm across the ground. The pulses would be electromagnetic, not a noise you could hear without instruments. If there were an atmosphere, some interactions might produce physical effects, but the pulsar's radio waves would not simply become a spooky knocking at the door. The name Poltergeist is wonderful, but the real disturbance is gravitational and electromagnetic. It is quieter than folklore and more severe than folklore. The planet does not hear the pulsar, it endures it. To orbit a pulsar also means living with an unusual sky beyond the central star. Because Lich is not bright in visible light like the sun, other stars might remain visible even when the pulsar is above the horizon, depending on any atmosphere and surface illumination. The sky might be a permanent star field, interrupted by a tiny compact source, and perhaps by radiation-driven glows. If there were no atmosphere, the stars would not twinkle. They would stand sharp and cold. From such a world, the universe might feel exposed, as if the sheltering warmth of an ordinary star had been removed. The central object would be physically dominant but visually modest, a tiny remnant ruling a system not by brightness but by gravity and radiation. This contrast is one of the strangest emotional features of pulsar planets. Around the sun, power looks powerful, the sun dominates the sky, it blinds, warms and fills the day. Around a pulsar, power may be hidden in compactness. Lich is small to the eye but enormous in consequence. It tells us that size in the sky is not the same as importance. A neutron star can be physically tiny and still anchor planets, emit beams across the galaxy, and reveal itself through timing precise enough to detect worlds. Poltergeist orbits an object that may look like almost nothing, but that almost nothing is the crushed core of a star. The planet's orbit also places it in a system where the central star's past cannot be separated from its present. The supernova that created the neutron star may have occurred long before the planets formed, if they are second-generation worlds, or it may have reshaped whatever was there before. Either way, orbiting Lich means orbiting not only a remnant but a history. The planet's material, its orbit, and perhaps its entire existence are tied to the violent path that led to the pulsar. This is very different from Earth's relationship with the Sun. Our Sun has changed over time, yes, but it has not died and left us circling its core. Earth's story belongs to a star in its long, stable middle age. Poltergeist's story belongs to a system after the central star's main life has ended. That is why the phrase zombie planet carries more meaning than a spooky nickname. Poltergeist is not alive after death, of course, but it belongs to an after-death system. It is a planet around a stellar corpse. It may have formed from debris after catastrophe. It may be made from material gathered under conditions that seem more like aftermath than birth. Its year continues around an object whose original star has already passed through its most violent ending. In that sense, Poltergeist is not simply orbiting a pulsar. It is orbiting the fact that stars can die and still leave structure behind. From a scientific perspective, that makes pulsar planets valuable. They test the limits of planet formation and survival. They ask whether disks can form around neutron stars. They ask whether rocky worlds can assemble in high radiation environments. They ask how stable planetary systems can be around compact remnants. They also remind us that planets do not require a sun-like star to exist. They require material, gravity, and time. Habitability is a narrower question. Existence is broader. Poltergeist exists in a place that would be deeply hostile to Earth life, but its existence alone is enough to stretch our definition of where planets can be. It is important, though, not to imagine pulsar planets as common just because this one was found early. Pulsars themselves are not the most likely places to find planets, and only a small number of pulsar planets are known compared with the thousands of exoplanets around ordinary stars. PSR B1257+12 remains special because it is rare. Its planets are not the typical outcome we see in exoplanet catalogues. They are an exception that teaches us something. Sometimes exceptions are more revealing than ordinary cases, because they show where the boundaries are. Poltergeist tells us that the boundary for planets extends farther into the strange than we might have expected. As we sit with all of this, orbiting a pulsar begins to feel like a combination of contradictions. The planet has a stable orbit, but the environment is violent. The central star is dead, but active. The system is dark in visible light, but intense in radiation. The planet is unseen, but its gravity is measured. The star is small, but dominant. Time there is marked by a millisecond pulse in a 66-day year. It is not chaos, and it is not comfort. It is order in the ruins. That may be the clearest way to understand Poltergeist's situation. It is a world moving through ordered danger. Every orbit is predictable in the broad sense. Every year carries it around Lich. But the star it orbits is a compact remnant with a harsh electromagnetic presence. If Earth's orbit feels like a path around warmth, Poltergeist's orbit feels like a path around a warning. The planet does not need to be habitable to be fascinating. It only needs to be real, and it is real enough to tug on the pulse of a dead star. And once we understand what it means to orbit a pulsar, the next puzzle becomes even harder to avoid. How did such a system come to exist at all? By now, the strangest part of Poltergeist is not simply that it orbits a dead star. It is that it belongs to a whole small planetary system that, at first glance, seems as if it should not be there at all. A single odd object might be easier to explain. A captured rock, perhaps. A leftover fragment. A survivor tossed into a strange orbit by some violent past event. But Lich does not have only one known companion. It has Draugr, Poltergeist and Phobator, a compact family of worlds moving in orderly paths around a neutron star. That is what makes the system so difficult and so fascinating. It is not only a planet in the ashes, it is a set of planets in the ashes, arranged with enough structure that their orbits can be measured, modelled, and watched through the tiny shifts they create in the pulsar's timing. The problem begins with the birth of the pulsar. A neutron star forms when a massive star reaches the end of its life and its core collapses. The outer layers explode outward in a supernova. That word can sound almost clean because we hear it so often in astronomy, but a supernova is not tidy. It is not a candle going out. It is a star tearing itself apart. The explosion throws enormous amounts of material into space. The energy released can outshine entire galaxies for a short time. Anything nearby would face blast waves, radiation, and the sudden loss of mass from the central star. Orbits that had once been stable could become unstable. Planets could be scorched, stripped, shattered, or thrown away into interstellar space. So when astronomers found planets close to PRB 1257+12, they were not just finding worlds, they were finding a challenge. How can a planetary system exist around the remnant of an event that should have ruined planetary systems? A simple survival story is difficult. Suppose the original massive star had planets before it died. Massive stars can have disks when they are young, and planets may form around many kinds of stars, so it is not impossible in the broad sense. But massive stars live short, violent lives compared with the Sun. They emit intense radiation even before they die. Their winds are strong. Their final explosion is catastrophic. If planets formed close to such a star, they would have spent their early existence under harsh conditions and then faced the supernova. The explosion would remove a large amount of the star's mass quickly. When the central mass changes suddenly, planetary orbits can expand, distort, or become unbound. A planet that once moved in a neat circle may find that the gravitational anchor has changed beneath it. It is like swinging a ball on a string and suddenly cutting part of the string's tension. The motion does not politely continue as before. For distant planets, survival might be more possible. A planet far from the star could avoid being completely destroyed by the blast, although its atmosphere and surface might still be damaged. But the known planets around Lich are not distant outer worlds. Poltergeist orbits at about 0.36 astronomical units. Phobator orbits a little farther out. Draugr is closer in. These are compact orbits. They are not the kind of far, cold paths where an original planet might quietly ride out. The death of a massive star with only a very bad day and some long-term orbital confusion. Their current arrangement looks too close, too orderly, and too linked to be a simple set of survivors from before the supernova. That does not make survival absolutely impossible in every version, but it makes it a hard explanation to accept by itself. There is another issue. The planets are small, terrestrial-scale bodies, not massive gas giants. If they had existed before the supernova, they would have had to form around a massive star, survive the star's intense earlier radiation, survive the explosion, and end up in close, stable orbits around the neutron star remnant. Each step adds difficulty. Science does not reject an idea just because it is difficult, but it does begin to prefer other ideas when the difficulties pile up like laundry on a chair. The more we look at Lich's planets, the more they seem less like original planets that endured everything unchanged, and more like worlds that formed after the main disaster, from material that settled around the neutron star. That idea is called second-generation planet formation. It means the planets did not form with the original star in the normal young star disk. Instead, they formed later from a disk around the compact remnant. This may sound exotic, but the basic physics of disk formation is common. When material orbits a central object and has angular momentum, it can flatten into a disk. Disks appear around young stars, around black holes, around white dwarfs, and around stars that are exchanging mass with companions. A disk is one of the universe's favourite ways to organise messy material. Give gas and dust a central object and enough rotation, and the material often spreads into a rotating sheet. In that sheet, particles can collide, settle, stick, and grow. Under the right conditions, planets can form. For PSR B1257+12, the question becomes where such a disk came from. One possibility is supernova fallback. In a supernova, not every bit of material necessarily escapes forever. Some matter can fail to reach escape speed, slow down, and fall back toward the newborn neutron star. If that fallback material has enough angular momentum, it can form a disk. This disk could cool, condense solids, and provide the raw material for planets. It is a compelling idea because it connects the planets directly to the star's death. The same violent event that made the neutron star may also have left behind the material that later formed Draugr, Poltergeist, and Phobator. In this picture, Poltergeist really is a planet in the ashes, assembled from the leftovers of the explosion. But fallback disks have their own problems. The disk must have enough mass in the right place. It must survive the early radiation and energetic behaviour of the neutron star. It must cool fast enough for solids to form. The solid material must become concentrated into the region where the planets are now. If the disk spreads too far, or loses too much material into the neutron star, it may not build the observed planets. If it does not form enough solids, there is nothing substantial from which to make a super-Earth. If gas remains too long, it may behave differently, but many models suggest gas around a pulsar would disappear quickly compared with ordinary protoplanetary disks. That makes gas giants unlikely and helps explain why the known planets are small and rocky rather than Jupiter-like. Still, making the exact compact arrangement of PSR B1257+12 is not trivial. The system is not just asking for planets. It is asking for planets in the right places, with the right masses, and with orbits that survived over long times. Another possibility involves a companion star. Many millisecond pulsars are thought to have been spun up by accreting matter from a companion. A neutron star in a binary system can pull gas from a nearby star. As that material falls in, it transfers angular momentum and can spin the neutron star faster and faster, turning it into a millisecond pulsar. PSR B1257+12 spins in about 6.2 milliseconds, which fits the general idea of a recycled pulsar, one that was accelerated by past accretion. If there was once a companion, then the planets may be connected not only to the original supernova, but to a later episode of interaction. The companion might have lost mass, been disrupted, evaporated, or merged in a way that created a disk around the neutron star. From that disk, planets could form. This scenario has an advantage. A companion can provide a lot of material. It also fits the fact that many millisecond pulsars have binary histories. In some versions, a white dwarf companion may have been disrupted, leaving a disk rich in carbon and oxygen. In others, a normal star or the remains of one may have supplied material during a complicated exchange. The details vary, and researchers do not all agree on one final answer. That is important. The formation of the PSR B1257+12 planets is still a puzzle, not a solved household appliance with all the screws neatly accounted for. But the companion disk idea is attractive because it gives the system a way to rebuild after the supernova, using material delivered or rearranged later. The phrase "should not have survived" therefore has two meanings. First, if planets existed before the supernova, they should have had a terrible chance of remaining in the compact orbits we see now. Second, if the planets formed afterward, then it is not the planets that survived the supernova, but the possibility of planet formation that survived. The system may not be a group of worlds that lived through the star's death. It may be a group of worlds that were born because the star's death and later history created the ingredients for a new disk. That is a very different kind of survival. It is not the survival of the same objects. It is the survival of structure, of the ability of matter to gather again. This is one of the deep lessons of the Lich system. Catastrophe does not always leave only emptiness. A supernova destroys, but it also distributes material. Accretion can be violent, but it can also create disks. Debris can be chaotic at first, but gravity can sort it. Collisions can break objects apart, but they can also build larger ones. Over enough time, the aftermath of a disaster can become a new architecture. That does not make the disaster gentle. It means the universe is very good at continuing. It does not pause after an explosion and say, well, that was enough activity for now. Matter keeps moving. Gravity keeps pulling. Orbits begin again if conditions allow. The arrangement of Poltergeist and Phobator gives us more clues. These two larger planets have similar masses and relatively close orbital spacing. Their orbital periods are near a 3:2 relationship, which means their motions have a repeating gravitational pattern. That kind of arrangement is not proof of a simple origin, but it is suggestive. Planets forming in a disk can migrate, interact, and settle into resonances or near resonances. Their mutual gravity can shape the system. Around PSR B1257+12, the interactions between these planets are strong enough to be measured in the pulsar timing. This makes the system feel less like a random collection of captured bodies and more like the result of a shared formation process. Capture is another idea that sometimes comes up when planets appear in odd places. Could Lich have simply captured planets that formed elsewhere? In space, objects can be exchanged during close encounters, especially in dense stellar environments. But capturing multiple small planets into close, stable, well-arranged orbits around an isolated pulsar would be extremely difficult. Space is big, encounters are rare, and planets do not simply drift into tidy orbits because it would make a nice story. To capture an object, energy must be removed from the system in some way. Otherwise, the object comes in and leaves again. Capturing one planet is hard enough. capturing a small family in compact orbits is much harder. So although capture is a useful thought experiment, it is not usually the preferred explanation for PSR B1257+12. What about the small inner planet Draugr? Its mass is tiny compared with Earth, and it orbits closest to the pulsar. Its presence adds another layer to the formation puzzle. A disk capable of making the two larger planets might also leave behind smaller bodies closer in. Or Draugr might represent a leftover embryo, a remnant from the same formation process, or a body whose growth was limited by the distribution of solids in the disk. In ordinary planet formation, not every object becomes a large planet. Some remain small. Some are scattered, some are swallowed. Some become asteroids, moons, or debris. Around Lich, we see only what the pulsar timing has revealed clearly enough, but there may also be smaller debris that remains undetected. The known system may be the visible skeleton of a more complicated past. The survival problem also depends on timing in a broader sense. How long after the supernova did the planets form? If they formed quickly, then the disk had to cool and produce solids in a harsh young pulsar environment. If they formed later, then the disk material had to persist or arrive through a later interaction. If a companion was involved, the system may have gone through a long binary phase before the planets assembled. Each timeline creates different expectations. A fallback disk might be connected to the immediate aftermath of the supernova. A companion disruption might happen much later. A white dwarf neutron star merger scenario would create a different chemical composition and a different disk evolution. The planets we see now are the final page of a long story whose earlier pages are partly missing. That missing history is part of what makes the system scientifically valuable. We cannot rewind PSR B1257+12 and watch it happen. We cannot observe the supernova that made it. We cannot see the disk that may have formed the planets if it existed. We have the current system, the pulsar's properties, the planetary masses and orbits, and the physics of what could produce them. From those pieces, researchers build models. They ask whether a fallback disk can place enough solids in the right region. They ask whether a disrupted companion can supply the material. They test how planetary embryos would grow and scatter. They compare simulations with the observed masses, eccentricities, and spacing. Sometimes the models work well in one way and fail in another. That is not a failure of science. That is science doing its job, narrowing the path through a difficult landscape. One reason gas giants are unlikely in this system is the short lifetime of gas in many pulsar disk models. Around young sun-like stars, gas can remain for millions of years, giving giant planets time to gather large envelopes. Around a neutron star, the environment can remove gas much faster. If the gas dissipates quickly, rocky planets can still form from solids, but Jupiter-like planets struggle. That matches what we see. The known planets are terrestrial scale, not gas giants. Poltergeist is several Earth masses, large enough to be called a super-Earth, but not massive enough to be a giant. Phobator is similar. Draugr is tiny. The system looks like a compact set of solid worlds, exactly the kind of outcome we might expect from a debris-rich, gas-poor disk around a pulsar. Still, there is a difference between matching the broad picture and explaining every detail. Models have to reproduce the compactness of the system. They have to explain why the planets are where they are. They have to account for their low eccentricities, their inclinations, and their mutual interactions. In some simulations, planets form but end up too spread out. In others, the amount of solid material is not right. Some scenarios require rapid dust sedimentation as the disk cools, so that solids concentrate into the region where planets can grow. These are technical issues, but they matter because they decide whether an idea is merely possible or truly persuasive. The system is a laboratory for planet formation under strange conditions, and laboratories are allowed to be demanding. There is also the question of why pulsar planets are rare. If neutron stars can form disks and disks can form planets, Why do we not see many systems like Lich? Searches around pulsars have not revealed large numbers of similar planets. That tells us the process must be uncommon or difficult. Perhaps fallback disks rarely have the right mass and angular momentum. Perhaps many disks are destroyed by the pulsar's radiation. Perhaps planets form only in special cases involving companion disruption or mergers. Perhaps the planets are there in some systems but below our detection limits, although pulsar timing is very sensitive in many cases. The rarity of systems like PSR B1257+12 makes it more important, not less. It is not an everyday example. It is a rare, successful outcome of an unlikely process. This rarity also gives the system a slightly lonely feeling. Around ordinary stars, planets are everywhere. The Milky Way is full of them. Red dwarfs have planets. Sun-like stars have planets. Giant stars have planets. White dwarfs may have debris from broken planetary systems. But pulsar planets remain unusual. Lich and its family stand out like a small settlement in a harsh desert. The fact that they exist shows the process can happen. The fact that we do not see many others shows it is not easy. Nature found a narrow path, and Poltergeist is moving along it. From the planet's point of view, if a planet can be said to have a point of view, none of this history matters in a conscious way. Poltergeist simply orbits. Its rocks do not remember whether they formed from fallback or from a disrupted companion. Its gravity does not explain itself. But to us the history matters because it changes the meaning of the world. If Poltergeist formed from fallback, it is a direct child of the supernova's remains. If it formed from companion debris, it is a product of a later stellar interaction, perhaps built from the body of another star. If it somehow survived from before the explosion, it is one of the most battered survivors imaginable. In every case, the planet is tied to violence. Its calm orbit today is the result of a past that was anything but calm. There is something deeply interesting about calm after violence. Astronomy is full of it. The moon may have formed from a giant impact, and now it raises tides with quiet regularity. The rings of Saturn may come from broken bodies, and now they appear as delicate bands. Heavy elements are made in stars and explosions, and now they sit in rocks, oceans, and living cells. The universe often turns collision into structure. Lich's planetary system is another example, but with the volume turned up. A star died. A neutron star remained. A disk may have formed. Solids gathered. Planets emerged. Now those planets move in predictable orbits, and their gravitational tugs are recorded by the dead star's pulse. That is why saying the system should not have survived is partly true and partly too simple. The original arrangement probably did not survive, at least not in any easy form. The massive star's death likely erased or transformed what came before, but the system we see now may not be a survivor in the ordinary sense. It may be a replacement, a second planetary system built from the wreckage or from material supplied after the wreckage. In human terms, we might call that rebuilding. In astrophysical terms, it is disk evolution, accretion, condensation, and planetary assembly. The physics is less sentimental, but the result is still remarkable. Poltergeist, Phobator, and Draugr also remind us that planets are not delicate ideas. Individual planets can be destroyed, of course, but planet formation as a process is robust. It can operate in young stellar nurseries, around dim red dwarfs, in binary systems, and perhaps even around compact remnants. It needs material and the right conditions for growth. It does not require a peaceful origin story. This matters because it broadens the search for planets and deepens our understanding of how matter organizes itself. If planets can form around a pulsar, then planet formation is not a rare trick reserved for gentle places. It is one of the universe's recurring habits. At the same time, this does not mean such planets are likely to be alive. Habitability is a different and far stricter question. A pulsar planet may be a triumph for formation, but a disaster for biology. Radiation, atmosphere loss, lack of ordinary sunlight, and the system's violent history all work against surface life as we know it. There are speculative discussions about whether thick atmospheres or subsurface environments could protect life around some pulsars, but Poltergeist is not a world we can casually place in the same category as Earth. It is better understood as a planet that teaches us about survival of structure, not necessarily survival of organisms. It is a world that says matter can regroup, not that gardens can bloom under every beam, and so the system remains balanced between two impressions. One impression is harsh. These worlds orbit a stellar corpse in a radiation-filled environment after an explosion or stellar interaction that should have made planet building unlikely. The other impression is orderly. The planets move in stable paths, their masses can be measured, their interactions can be modelled, and their existence proves that even a pulsar can have a planetary family. Both impressions are true. That is what makes Lich's system so rich. It is not merely frightening. It is not merely beautiful. It is a working system built in a place where our first instincts say it should not work. It is tempting to imagine Poltergeist as simply dark. A planet around a dead star must be dark, we might think, because the star is no longer a sun-like furnace spreading warm visible light across its worlds. And in one important sense, yes, Poltergeist probably does live in a kind of darkness that would feel deeply unfamiliar to us. But darkness is not the same as calm. A cave is dark. A quiet bedroom is dark. The space around a pulsar can also be dark to human eyes, but it is not quiet in the physical sense. It is crossed by radiation, charged particles, magnetic influence, and the repeated sweep of a dead star's beam. So the strange sky of Poltergeist would not be strange only because it lacks a golden sunrise. It would be strange because the thing at the centre of its sky is small, dense, fast, and dangerous in ways that ordinary starlight does not prepare us for. On Earth, the sun dominates everything. Even when clouds hide it, even when night falls, even when we are indoors and pretending we have a healthy sleep schedule, the sun is still the clock behind the weather, the seasons, the plants, and the temperature of the planet. Its light scatters through our atmosphere and makes the sky blue. Its warmth moves air and water. Its rhythm gives us morning and evening. Poltergeist has no such ordinary parent star. It orbits Lich, PSR B1257+12, a millisecond pulsar. Lich is a neutron star, the collapsed core of a massive star that died long ago. It is tiny compared with the Sun, but massive, fast-spinning, and magnetically active. It does not gently pour sunlight over its planets. It sends out energy in a much less comfortable form. If you try to picture the sky from Poltergeist, the first thing to remove from the scene is the large round sun. There would be no broad yellow disk climbing above the horizon, no warm morning light spilling across the ground, no soft sunset turning clouds orange unless the planet somehow has clouds and an atmosphere capable of doing something very unusual with the radiation it receives. The pulsar itself would be physically small, perhaps appearing as a point-like object rather than a large star in the sky. That point, however, would be the collapsed core of a star. It would have more mass than the Sun, packed into a sphere only about the size of a city. It would be a reminder that space does not always make important things look important. Sometimes the most dangerous object in the sky is not the largest looking one. Sometimes it is a tiny point with the gravity of a star and the behaviour of a spinning lighthouse. But this lighthouse does not shine like a lighthouse on Earth. A normal lighthouse sends visible light across water, so ships can avoid rocks, which is helpful and polite. A pulsar sends beams of electromagnetic radiation from regions near its magnetic poles, and as it rotates, those beams sweep through space. If the beam crosses our line of sight, we detect pulses. If a beam crosses Poltergeist, then parts of the planet could be struck again and again with a rhythm set by the dead star's rotation. PSR B1257+12 spins in milliseconds. so the pulse is not a slow flash that would feel like a lighthouse blinking at a harbour. It would be rapid, almost continuous from a human perspective, a relentless strobe of energy far too fast for the eye to separate, assuming the eye had any business being there in the first place, which it absolutely does not. The radiation from a pulsar can include radio waves, X-rays, gamma rays, and energetic particles, depending on the pulsar and the specific processes in its magnetosphere. These forms of radiation do different things. Radio waves can cross space and reveal the pulsar to our telescopes. X-rays and gamma rays carry much more energy and can damage atoms and molecules. Charged particles can slam into atmospheres, strip gases away, break chemical bonds, and create intense auroras if there is a magnetic field and enough gas for them to interact with. Around Earth, the Sun also sends radiation and charged particles, but we are protected by a thick atmosphere and a magnetic field. Our planet is not exposed bare to the solar wind. Poltergeist may not have that luxury. If it has no substantial atmosphere, the surface would be directly exposed to space. If it does have an atmosphere, that atmosphere would have to survive constant attack from the pulsar environment. This is where the darkness of Poltergeist becomes different from ordinary darkness. Imagine standing on a moon with no atmosphere, where the sky is black even during the day because there is no air to scatter light. That is already an alien experience compared with Earth. Now replace the Sun with a compact neutron star. The visible light may be weak, but the dangerous radiation may still be strong. The ground could be dark to the eye while being bombarded by forms of energy that the eye cannot see. It is a little like walking into a room that looks unlit and being told that the real problem is not the lack of lamps, but the invisible machinery humming in the walls. A place can be visually dim and physically severe at the same time. If Poltergeist has no atmosphere, its sky would be nearly black. Stars would not twinkle because twinkling is caused by Earth's atmosphere bending starlight. The Milky Way might stretch overhead with sharp, steady detail, depending on what direction the planet's surface faced and how much glare or radiation came from the pulsar. The horizon would be hard. Shadows, if there were enough visible light to cast them, could be sharp. There would be no wind, no clouds, no blue scattering, no thunder, and no sound carried through the air. The pulsar's pulse would not be something you could hear. Radio waves are not sound waves. They do not make a knocking noise on the rocks. So although the planet is named Poltergeist, the real planet would not necessarily be noisy. Its disturbance is not a spooky rattle in the walls. It is gravity and radiation, quieter than a ghost story, and much less forgiving. If Poltergeist has an atmosphere, the sky becomes more complicated. An atmosphere could scatter light, absorb radiation, glow under particle bombardment, and move heat around the planet. But keeping an atmosphere around a pulsar is difficult. High-energy radiation can heat the upper atmosphere and allow gas to escape. Charged particles can strip molecules away. Lighter gases, such as hydrogen and helium, are especially vulnerable. A planet with several Earth masses has stronger gravity than Earth if its radius is not too large, and that stronger gravity could help it hold on to heavier gases. But gravity is only part of the story. The atmosphere would also need to resist erosion over enormous spans of time. Around a pulsar, that is a hard job, rather like trying to keep a hat on during a storm, except the storm is made of particles from a dead star and the hat is your entire sky. Some scientific work has explored whether neutron star planets could, under certain conditions, hold thick atmospheres and even maintain surface temperatures where liquid water might exist. That idea sounds surprising, and it should be handled carefully. It does not mean Poltergeist is likely to be a pleasant world. It means that, in some models, if a planet has a very dense atmosphere, and if the pulsar wind interacts with that atmosphere in the right way, energy could be deposited and redistributed. A thick atmosphere could also provide shielding from radiation at the surface, but these models depend on uncertain details, including the strength and behaviour of the pulsar wind, the planet's atmosphere, and how energy is absorbed. So it is not honest to say Poltergeist is habitable. It is more accurate to say that scientists have considered the physics of such worlds, and the answer is not as simple as pulsar equals impossible in every imaginable case. The universe enjoys making simple answers uncomfortable. For Poltergeist itself, we do not know whether it has air. We do not know whether it has a magnetic field. We do not know its surface pressure, its rotation, its geology, or whether any gases remain around it. We know its mass and orbit far better than we know its weather. That can feel frustrating, but it is also normal in exoplanet science. Many exoplanets are known first as masses, radii, or orbital periods, and only later, if we are lucky, as physical places with atmospheres or temperatures. Poltergeist is even harder because it orbits a pulsar, and the usual methods for studying planetary atmospheres around bright stars do not apply in the same way. There is no comfortable sunlight filtering through the edge of its atmosphere during a transit that we can easily examine. The planet is real, but its sky is mostly unknown. Still, we can reason from the environment. If Poltergeist is a rocky super-Earth with little or no atmosphere, its surface would probably be exposed to radiation and micrometeorite impacts. Without air or water, erosion would be very different from Earth. Craters could last for long periods. Dust might become electrically charged under particle bombardment. Surface minerals could be altered by radiation over time. If the planet has internal heat, perhaps it has volcanism or tectonic features, but that is uncertain. A world several times Earth's mass could retain heat well, but its history, composition and interior structure matter. It may be geologically active, or it may be a hard, cold body whose most dramatic changes come from outside. The pulsar would not care either way. It would continue spinning. If the planet has a thin atmosphere, the surface might experience a strange kind of space weather. Charged particles could stream along magnetic field lines if Poltergeist has a magnetosphere. Auroras could form where particles enter the atmosphere, perhaps not in the familiar green curtains we see on Earth, but in colours and wavelengths depending on the gases present. Some emissions might be invisible to human eyes. The sky could glow faintly in ultraviolet or X-rays. The atmosphere might be constantly escaping in a long tail shaped by the pulsar wind like a cometary wake. This is speculative, but it is grounded in known processes. Planets near energetic stars can lose atmospheres. Charged particles can make gases glow. Magnetic fields can funnel energy toward poles. Around Poltergeist, those processes would be governed by a dead star's engine rather than a living star's sunlight. There is another odd possibility. If the pulsar's beam does not strike Poltergeist directly, the planet might still be affected by the broader pulsar wind and high-energy environment. The beam we see from Earth is only one direction in which radiation is emitted. The pulsar's magnetosphere and particle outflow can shape a region around it more generally. So the question is not only, does the lighthouse beam sweep across the planet? It is also, what is the entire space environment like around the pulsar? That environment may vary with distance, magnetic geometry, and the pulsar's age and spin-down power. PSR B1257+12 is an old millisecond pulsar, not a newborn supernova remnant screaming with the energy of youth, but it is still a pulsar. It still has a magnetic field. It still emits pulses. It still influences its surroundings in ways no ordinary planet around a quiet star would have to deal with. The darkness also changes the emotional idea of a day. On Earth, day and night are obvious. They are so familiar that we build language around them. Morning means beginnings. Evening means winding down. Night means rest, or at least it should, unless someone has invented a new show with 12 episodes and poor self-control has entered the room. But on Poltergeist, a day may not be defined by a warm star rising and setting. The planet's rotation is unknown, the pulsar's visible light may be weak. The most important radiation may come in pulses or particle streams that do not resemble daylight. If the planet rotates, different regions might face the pulsar and turn away. but whether that creates anything like day and night depends on what kind of energy reaches the surface and whether an atmosphere scatters or transports it. A day on Poltergeist might be more of a changing exposure pattern than a familiar cycle of light and dark. The year at least is clearer. Poltergeist goes around Lich in about 66.5 Earth days. That orbit is short by our standards. One Poltergeist year passes in a little over 2 months. But if you lived there, again with the very large imaginary safety equipment required, you might not feel the year through seasons the way we do. Seasons depend on axial tilt, atmosphere, heat transport, and the type of stellar energy received. Without those, the year is simply an orbital rhythm. It matters gravitationally. It matters for the planet's position in the system. It matters for the timing signals we detect from Earth. But it may not bring spring flowers, summer heat, autumn leaves, or winter snow. The calendar can move quickly without making the world feel alive. The sky would also carry the presence of the other planets, although seeing them would depend on their brightness and the observing conditions from the surface. Phobetor and Draugr share the system with Poltergeist. From Poltergeist, Phobetor might sometimes appear as a neighbouring point of reflected or emitted light, if there is enough illumination to reveal it. Draugr, being smaller and closer to the pulsar, would be harder to notice, but even if they were invisible, their gravity would be part of the system's reality. Poltergeist and Phobetor are close enough in their orbital relationship that their mutual perturbations helped confirm their properties. So the sky may look sparse, but the gravitational environment is not lonely. The planets are in conversation through gravity, even if no eye could pick them out easily. One of the hardest things to imagine is what colour the sky would be. The answer may be black if there is no atmosphere. If there is an atmosphere, the colour depends entirely on its composition, density, and the radiation striking it. Earth's blue sky is not universal. Mars has a dusty reddish sky that can turn bluish near sunsets. Titan has an orange haze. Venus has thick clouds that hide the surface from direct view. Gas giants have banded skies of clouds and storms. Poltergeist, if it has a sky at all, could be stranger still. High-energy radiation might create chemical hazes. Particle bombardment could produce glows. If the atmosphere is thin, the sky could remain dark overhead while the horizon shows faint scattering. If it is thick, the pulsar itself might be hidden behind layers of gas, while the upper atmosphere absorbs the worst radiation. A thick atmosphere would make the surface more protected but not necessarily friendly. Pressure, chemistry, and temperature could be extreme. There is a practical lesson here. Habitability is not only about distance. We often hear about planets in the right zone, the right orbit, the right distance for liquid water. But Poltergeist reminds us that the kind of star matters just as much as the distance. Around a sun-like star, visible and infrared light provide energy in forms that atmospheres and surfaces can manage in familiar ways. Around a red dwarf, flares and tidal locking become major concerns. Around a pulsar, radiation and particle winds dominate the discussion. The same orbital distance can mean completely different things depending on the central object. A planet cannot be judged by the size of its orbit alone. It has to be judged by the whole environment. And Poltergeist's environment is a good example of why the universe can be both ordered and hostile. Its orbit is stable, its mass is measured, its presence is real. Yet a stable orbit does not guarantee a gentle surface. The Moon has a stable orbit around Earth, and still it is airless, harsh, and exposed. Mercury has a stable orbit around the Sun, and still experiences extreme temperatures and a battered surface. Poltergeist has a stable orbit around a pulsar, and that stability says nothing simple about comfort. It only means gravity has found a pattern that lasts. If we let the imagination move carefully, without pretending we know more than we do, a possible scene appears. A rocky super-Earth under a black or dim sky. A tiny central object, perhaps not bright to the human eye, but physically dominant. A rapid pulse of radiation crossing space. A surface altered by high-energy particles. Maybe a thin atmosphere glowing faintly, maybe no atmosphere at all, the stars overhead sharp and steady, neighbouring planets hidden in the dark known more by gravity than by sight. No birds, no wind in any familiar sense, no blue daylight, no warm afternoon. Just a world moving through the aftermath of a stellar death, under a sky where danger may arrive invisibly. And yet, it is not just a scene of emptiness. There is information there. The surface, if we could study it, would tell us about its origin. The minerals could reveal whether it formed from supernova fallback companion debris or some other disk. The atmosphere, if any, could tell us how planets respond to pulsar radiation. The magnetic environment could show how super-Earths interact with neutron star winds. Even a lifeless poltergeist would be scientifically rich. A hostile world can still be a valuable world. In astronomy, interesting and habitable are not the same word, and poltergeist is a very good reminder of that. Its darkness also makes its discovery feel more impressive. We did not find it because it shone, we found it because it tugged on time. That is still the quiet miracle at the centre of the story. A dark planet around a dead star, possibly airless, possibly radiation battered, invisible in ordinary light, revealed by the way it makes a pulsar's pulses arrive a little early and a little late. The strange sky of Poltergeist is mostly hidden from us, but its gravity is not. In a system where light may not tell us much, timing becomes the guide. So Poltergeist is dark, but not silent. It is not silent because it participates in the pulsar's timing. It is not calm because the radiation environment may be severe. It is not familiar because its star is a neutron remnant rather than a living sun. If Earth's sky feels like an atmosphere wrapped around warmth, Poltergeist's sky, if it has one, would be a boundary between rock and the machinery of a dead star. That boundary may be thin, thick, stripped, glowing, or gone. We do not yet know. What we do know is that the planet's present is shaped by the same thing that revealed it, the pulse of Lich. Poltergeist is not alone in the dark. That may be one of the most important things about it. If this story were only about one strange planet orbiting one dead star, it would already be unusual enough to deserve a quiet evening of attention. But around Lich, the dead star PSR B1257+12, there is a small family of worlds. They are not warm, bright, familiar siblings under a generous sun. They are stranger than that. They move around a pulsar, a collapsed stellar core in orbits that were discovered through timing, gravity, and patience. And their names sound as if someone in astronomy briefly opened a book of old nightmares and decided, quite reasonably, that the system had earned the theme. Closest in is Draugr, small and faint in the records, a little world with only a tiny fraction of Earth's mass. Then comes Poltergeist, the super-Earth we have been following, tugging on the pulsar's pulse with enough strength to reveal itself from far across space. Beyond it moves Phobator, another super-Earth, close enough in character and orbit to Poltergeist that the two seem less like random objects and more like members of the same difficult family. Draugr is the smallest of the known planets in this system, and in some ways its smallness makes it especially interesting. It is not a giant. It is not even Earth-sized. It is a tiny terrestrial planet, much less massive than Earth, orbiting Lich in about 25 Earth days. That means it travels closer to the pulsar than Poltergeist does, circling the dead star in a tight little path. If Poltergeist is a strange world in the ashes, Draugr is more like a surviving ember, a small piece of planetary architecture in a place where even larger worlds already feel surprising. Its name comes from old stories of the undead, and while a planet cannot be undead in any literal sense, the name fits the mood of the system. Draugr belongs to a star after death. It belongs to a planetary family that should not easily exist. It is a small body moving in the gravitational shadow of a stellar corpse, and yet it is there, tracing its orbit again and again. Phobos, farther out than Poltergeist, is closer to it in mass and importance. It is another super-Earth, about 3.9 times Earth's mass, completing an orbit in roughly 98 Earth days. That makes it a near companion to Poltergeist in the architecture of the system. The two larger worlds are not just neighbours in a casual sense. Their orbits are close enough and their masses strong enough that they gravitationally disturb one another. These disturbances are tiny, but in pulsar timing, tiny disturbances can matter. The mutual pull between Poltergeist and Phobos helped astronomers confirm the reality of the planets and refine their masses and orbital arrangement. In a system discovered through a clock, even the planets' interactions become part of the ticking record. They tug on the pulsar, they tug on one another, and the pulse from Lich carries the evidence outward like a message written in time. This relationship between Poltergeist and Phobos is one of the clues that the system did not simply happen by accident. If you found one planet near a pulsar, you might imagine an unusual survivor or a captured object. If you find two substantial planets in related nearly circular, nearly coplanar orbits, and then a smaller inner planet as well, the story begins to look more organised. Not gentle, but organised. Their arrangement suggests that they may have formed together from a disk, the way planets usually form from rotating material around a central object. The difference is that this disk, if it existed, was not the ordinary protoplanetary disk around a young shining star. It was likely a disk around a neutron star, or around the system that became one, after an episode of death, disruption, or violent mass transfer. In other words, Draugr, Poltergeist, and Phobos may be siblings because they were built from the same strange reservoir of debris. That brings us to one of the most fascinating ideas in this entire story. A dead star can still make new worlds. At first, that sounds almost contradictory. Stars make planets when they're young, we usually think. A cloud collapses. A protostar forms. A disk of gas and dust surrounds it. Dust grains collide and stick. Planets slowly assemble while the star settles into its long, bright life. This is the familiar nursery picture. It is not simple, but it is at least comfortable. There is youth, material, growth, and order. A pulsar, by contrast, looks like the end of the line. It is the remnant after a massive star has exhausted its fuel, collapsed, and exploded. The nursery should be gone. The original disk should be long vanished. The system should have been swept clean or broken apart. And yet, around Lich, planets exist. So how can a dead star make new worlds? The answer begins with the fact that destruction often leaves material behind. A supernova throws matter outward, but not every scenario is perfectly clean. Some material may fall back toward the newly formed neutron star. If it has enough angular momentum, it cannot fall straight in. Instead, it can spread into a disk. This is called a fallback disk, and it is one of the main ideas astronomers have explored for pulsar planet formation. In such a disk, matter from the star's own explosive death could eventually cool, condense, and separate into solids. Those solids could gather into larger and larger bodies. The dead star would not be making planets by shining warmly on a young protoplanetary disk. It would be making them from its own aftermath, from material that failed to escape completely and settled back into orbit. That is a strange sort of rebirth. It is not gentle rebirth, and it should not be softened too much. A supernova is still a violent event. The early environment around a newborn neutron star can be harsh, hot, and energetic. A disk there would face radiation, magnetic influence, and rapid evolution. Gas might not survive long. Dust would need to form or settle quickly. The material would need to gather in the right region before it disappeared into the neutron star, spread too far outward, or was blown away. Still, under the right conditions, a fallback disk might create a compact system of rocky planets. That makes the Lich system feel less like a miracle, and more like a difficult but possible outcome of physics. Given enough debris, enough rotation, and enough time, gravity can begin building again. Another possibility is even more dramatic. Lich may once have had a companion star. Many millisecond pulsars are thought to be recycled, meaning they were spun up by accreting material from a companion. A neutron star can pull gas from a neighbouring star, gaining angular momentum and spinning faster until it becomes one of these incredibly rapid pulsars. If that happened in the history of PSR B1257+12, then the planets might have formed from material lost by the companion. The companion could have been stripped, disrupted, or even destroyed. Its remains could have formed a disk around the neutron star. From that disk, new solid bodies could have grown. In this picture, the planets are not only children of a dead star, they may be children of a dead partnership, made from material taken from or left behind by another star. Some models go further and explore whether a white dwarf companion could have been disrupted by the neutron star. A white dwarf is itself a stellar remnant, the dense leftover core of a star like the Sun after it has shed its outer layers. If such an object were torn apart by a neutron star, it could produce a disk rich in carbon and oxygen. Under the right circumstances, solids could condense and planets could form from that unusual material. That idea has led to speculation that the pulsar planets could be carbon-rich, perhaps very different in composition from Earth. But here, as always, we need to step carefully. These models are possible formation stories, not direct photographs of Poltergeist's interior. We do not know that these planets are diamond worlds or carbon planets. What we can say is that the system has inspired serious scientific attempts to explain how compact rocky planets might form from very non-ordinary disks around a neutron star. The important point is that all of these ideas share one theme. The planets are probably not simple first-generation worlds like Earth. Earth formed in the original disk around the young Sun. Poltergeist, Draugr and Phobator may have formed later, after the original star had already gone through a catastrophic transformation. They may be second-generation planets, built from material that was recycled through stellar death, fallback, disruption, or accretion. That makes them different from most planets we talk about. They do not belong to a calm beginning. They belong to an aftermath that became productive again. This can feel surprising because we often think of aftermath as empty. The fire burns out, the room cools, the story ends. But in astronomy, aftermaths are often full of ingredients. Supernovae scatter heavy elements. Stellar winds enrich space. Collisions make debris. Disrupted bodies form disks. Gravity does not mind that the material has a tragic backstory. It simply pulls. Dust grains collide. Fragments settle. Orbits shape themselves. In that sense, a dead star can make new worlds not because death is gentle, but because death rearranges matter. The universe is less interested in endings than we are. It treats every ending as a change in the available materials. Draugr shows how small pieces can remain part of the pattern. Its low mass may mean it is a leftover from the same planet-building process that made Poltergeist and Phobator. Perhaps it never had enough nearby material to grow larger. Perhaps its region of the disk was depleted. Perhaps it formed from a small cluster of solids close to the pulsar and remained tiny, while the outer embryos grew into super-Earths. In planet formation, size depends on location, timing, available material and collisions. Not every embryo becomes a full planet. Some remain small, some are lost, some are absorbed into larger worlds. Draugr may be a surviving clue to the inner part of the disk, a small body that tells us the planet-building process did not produce only the two larger worlds. Phobator, on the other hand, tells us about partnership. Its closeness in mass and orbital relationship to Poltergeist suggests a shared growth history. The two larger planets may have assembled from nearby regions of the disk, then interacted gravitationally as they settled into their current orbits. Their near 3-2 orbital relationship hints at past migration or formation in a compact disk where planets influenced one another. Resonances and near resonances are common signs of gravitational shaping. They do not automatically reveal every detail, but they tell us the worlds have not been moving in complete isolation. Poltergeist and Phobetor are siblings that continue to affect each other's motion, even now, long after their formation. There is a quiet beauty in that. Around a living star, planets can be linked by resonances, as some of Jupiter's moons are, and as many exoplanet systems are. Around a dead star, the same gravitational music can play. The instrument is stranger, but the rules still apply. Orbital periods, masses, inclinations, perturbations, all of these remain meaningful. Lich may be a pulsar, but its planets still move according to gravity. The system may have formed under extreme conditions, but once planets are there, they behave like planets. They orbit, they tug, they settle into long-term patterns if the configuration is stable enough. The laws of motion do not become spooky just because the names do. What might the early disk around Lich have looked like? We should imagine it cautiously, but not blankly. It may have been a compact, hot, rotating disk of gas and dust around the neutron star. In the fallback scenario, it would have contained material from the supernova's ejector. In the companion disruption scenario, it may have contained material from a star or white dwarf torn apart or stripped during the system's evolution. At first, it may have been too hot for ordinary solids to survive. As it cooled, dust could condense, heavier elements could become grains. Those grains could settle toward the midplane of the disk, where collisions are more likely. Over time, small solids could become larger bodies. If the gas disappeared quickly, the result would favour rocky planets rather than gas giants. That matches the known system because Lich has small terrestrial-scale planets, not a Jupiter wrapped around the dead star. Gas disappearing quickly is important. Giant planets like Jupiter and Saturn require a lot of hydrogen and helium, or at least a massive enough core to gather gas before the disk disperses. Around a pulsar, gas may be removed or accreted quickly, leaving solids behind. That means the planet-building process could be cut short in a way that produces rocky or metal-rich planets, but not giant ones. Poltergeist and Phobetor are super-Earths, substantial but not enormous. Draugr is tiny. The system looks like the solid remnant of a disk that had enough material to make terrestrial planets, but not the right conditions to make gas giants. It is not a miniature solar system. It is its own kind of compact remnant-born system. This also helps explain why dead star planet formation is rare. The conditions have to line up. You need material, you need angular momentum. You need the disk to survive long enough for solids to form. You need the solids to gather in the right place. You need the pulsar's radiation and magnetic activity not to destroy the process too early. You need the final planets to remain stable. That is quite a list, and the universe, while generous, is not always tidy. Many neutron stars may never receive the right disk. Others may have disks that disappear too quickly. Some may form debris but not planets. Some may form planets too small or too far to detect. So Lich's family is not expected to be common, and observations support that. Pulsar planets are rare compared with planets around ordinary stars. That rarity makes Draugr, Poltergeist and Phobetor feel like a special case, not a standard planetary recipe. There is another way to look at the three planets together. They are a record of a disk we can no longer see. The disk itself is gone, or at least no longer obvious. We do not observe a broad bright ring of material around PSR B1257+12 from which planets are still forming. The planets are what remain. Their masses and orbits are like fossils of the formation process. A paleontologist studies bones to infer an animal. An astronomer studies orbits to infer a disk. The planets are not just bodies, they are evidence. Draugr tells us something about the inner material. Poltergeist and Phobetor tell us about the region where larger bodies could assemble. Their near-coplanar orbits suggest a flattened disk origin. Their interaction tells us they grew as a connected system. The vanished disk still speaks through them. This makes the dead star feel less like a final object and more like a centre of transformation. Lich did not simply end a story. It became the gravitational anchor for another one. That is not the same as saying it is kind or life-giving. A pulsar is still harsh. Its radiation may strip atmospheres and make the surfaces of nearby planets extremely hostile, but planet formation does not require kindness, it requires physics. A world can form in a place where life would struggle or fail. The universe builds many things that are not for us. This may be one of the most useful thoughts in astronomy. Not every planet is a home. Some planets are records, some are experiments, some are reminders of processes we would never have imagined from Earth alone. Poltergeist's siblings help us avoid seeing it as a lonely oddity. Without Draugr and Phobetor, Poltergeist might feel like an isolated freak of circumstance. With them, it becomes part of a system. Its existence gains context. Phobetor shows that another large rocky world formed or survived in the same environment. Draugr shows that smaller bodies were also involved. The system becomes a family portrait taken in darkness, with the dead star at the centre and 3 planets arranged around it. The portrait is not visual but dynamical. We see it through timing, through the way each planet affects the pulsar's pulse. It is a family known by its fingerprints rather than its faces. If we let ourselves picture the system from far outside, it is almost too small to see. Lich is a compact object spinning rapidly. Draugr races close in. Poltergeist follows its 66-day path. Phobetor moves beyond it on a 98-day orbit. There may be other smaller debris we do not know about, perhaps asteroids, dust, or fragments below the timing detection threshold, or perhaps the 3 known worlds are mostly what remains. Around them, space is dark, crossed by radiation and the pulse. From Earth, the system is a set of arrival time deviations. From a godlike view, if such a view were possible, it would be a small gravitational machine made from aftermath. The idea that dead stars can make new worlds also echoes beyond this one system. White dwarfs, the remains of sun-like stars, are often found with polluted atmospheres, meaning they have swallowed rocky debris from their old planetary systems. Some white dwarfs have disks of broken asteroids or planetesimals. Neutron stars can have disks under rare circumstances. Even black holes can be surrounded by disks, though planets around them would be a different and speculative matter. The broad theme is that compact remnants do not always sit in empty space. They can interact with leftover material. They can tear bodies apart, gather debris, or become the centres of disks. And wherever disks exist, the question of planet formation begins to whisper nearby. Still, the Lich system remains one of the clearest and strangest examples. It does not merely have dust, it has planets. Not vague hints, not only fragments, but measured worlds. Draugr, Poltergeist, and Phobetor give form to the idea that second-generation planets can exist. They are not theoretical sketches on a chalkboard. They are bodies orbiting a real pulsar discovered through real-timing data. That is why the system continues to matter. It pushes planet formation into territory that once seemed nearly impossible. There is something quietly reassuring in the stubbornness of matter. Even after a star dies, even after an explosion or disruption, even after a system is stripped down to a compact remnant and debris, matter can still find structure. Not always, not easily, not in ways that produce comfort, but sometimes. Given the right disk, dust can settle. Given enough collisions, small pieces can grow. Given stable orbits, worlds can remain. The result may be a ghostly family around a dead star, but a family all the same. And so Draugr and Phobetor change how we understand Poltergeist. They show that it is not a single strange stone circling a dead star by chance. It is one member of a compact planetary system that likely formed through a shared history. Draugr, small and close, whispers of the inner disk. Phobetor, massive and neighbouring, pulls on Poltergeist and helps confirm the system's ordered structure. Poltergeist sits between them, the zombie planet in the ashes, not alone but surrounded by siblings that make the entire story deeper. Together, they tell us that a dead star can still gather material, still anchor orbits, still become the centre of new worlds. Poltergeist changed the search for exoplanets because it arrived from the wrong kind of place at exactly the right time. That is one of the most interesting things about it. Before planets around other stars became a normal part of astronomy news, before space telescopes filled catalogues with thousands of distant worlds, before we had become used to hearing phrases like hot Jupiter, super Earth, mini Neptune, lava planet, or ocean world candidate, there was a strange dead star in Virgo whose pulse did not arrive quite on schedule. Around that dead star, astronomers found planets. Not around a warm, sun-like star, not around a gentle young star with a bright dusty disk, not around something that looked like the solar system from a distance. The first confirmed planets beyond our solar system were found around a pulsar, the collapsed remnant of a star that had already died violently. If astronomy had been planning a tidy opening scene for the exoplanet age, this was not it. It was more like opening a quiet door and finding a laboratory, a haunted clock, and a planetary system all sharing the same room. That surprise mattered. For a long time, planets beyond the solar system were expected, but expectation is not the same as confirmation. Many people assumed other stars must have planets, because the solar system seemed unlikely to be completely unique. The ingredients of planets are common. Stars form in gas and dust. Disks should form around young stars. It made sense that other planetary systems existed, but actually proving it was hard. A planet beside another star is small, faint, and usually lost in the glare of its parent star. If you tried to see Earth from many light years away, next to the Sun, it would be like trying to spot a dust mote beside a searchlight from another country, while the searchlight is also moving and everyone involved has run out of biscuits. So for much of the 20th century, exoplanets lived in the realm of reasonable suspicion. Astronomers looked, argued, refined techniques, and waited for evidence strong enough to stay standing. The discovery around PSR B1257+12 helped change that. It showed that planets beyond the solar system were not only possible, not only likely, but measurable. The method was unusual, but the conclusion was firm. The pulsar's timing variations showed that planet-sized bodies were orbiting it. This was a shock, because a pulsar was not where most people expected the first confirmed exoplanetary system to appear. A pulsar is a neutron star, a compact remnant after a supernova. It is connected to death, collapse, radiation, and extreme physics. If planets could be found there, then the universe was not merely copying the solar system in other places. It was making planetary systems in settings that forced astronomers to think more broadly. Poltergeist and its siblings did not just add a few names to a list. They changed the size of the list that astronomy was willing to imagine. One of the most important changes was psychological, though science rarely admits how much psychology matters until after the equations are safe. Before the first confirmed exoplanets, planet hunting carried a certain burden. Astronomers were looking for something almost everyone believed existed, but belief was not enough. Claims had been made before, some had weakened, some had failed. A possible pulsar planet around another object had even been retracted after an error involving Earth's motion was found. So when PSR B1257+12 showed timing variations, the result had to be treated with care. But once the pulsar planets held up, once continued timing supported the planetary interpretation, the field changed. It was no longer a question of whether other planetary systems could be confirmed at all. They had been. The door had opened, even if the first room beyond the door was much stranger than expected. That first confirmed system also reminded astronomers that detection methods shape what we find. Pulsar timing is extremely sensitive because pulsars can be incredibly regular clocks. A tiny planet can make a tiny gravitational tug, and if the central clock is precise enough, that tug can appear as a tiny shift in pulse arrival time. around PSR B1257+12, those shifts revealed worlds. This was different from later methods that would dominate the exoplanet search. The radial velocity method looks for the wobble of a star by measuring shifts in its light. The transit method watches for a planet crossing in front of a star and blocking a small amount of light. Direct imaging tries to separate the faint planet from the bright star. Microlensing uses the bending of light by gravity when one star system passes in front of another. Pulsar timing belongs to the same family of clever indirect methods, but it is one of the most precise. It turns a dead star into a clock and a planet into a timing disturbance. That lesson carried forward. Exoplanet astronomy became a field built on indirect evidence. A planet does not have to be seen directly to be real. It can be measured through what it does. It can dim a star. It can pull a star. It can bend background light. It can disturb the timing of pulses. It can alter the timing of other transiting planets. This sounds obvious now, after decades of discoveries, but Poltergeist helped establish that confidence. The planet was not visible in a telescope image. It was not a dot beside a star. It was a pattern in time, and because the pattern matched orbital motion, it became a world. That is a powerful idea. It means a planet can be known by its consequences. There is something wonderfully practical about that. Science does not always require the universe to present itself in the way our senses prefer. We like pictures. Pictures are satisfying. A photograph of a planet feels immediate, even if it is only a few pixels. But many of the most important astronomical discoveries come from measurements that look, at first, less dramatic. A spectral line shifted by a tiny amount, a dip in brightness, a pulse arriving early, a pulse arriving late. These small clues can become planets, black holes expanding space, chemical compositions, atmospheres, and histories. Poltergeist belongs to that tradition. It told astronomers that exoplanet science would not be a field of simply looking and seeing. It would be a field of listening, timing, comparing, and trusting careful patterns. The discovery also widened the idea of what a planetary system could be. Before the exoplanet era, the solar system was our only detailed example. That is a dangerous position for science, because one example can feel like a rule, even when it is only a sample of one. Our solar system has small rocky planets inside, giant planets outside, mostly circular orbits, one main star and a certain kind of order. It is tempting to imagine that other systems would look broadly similar. Poltergeist interrupted that temptation immediately. Here was a planetary system around a pulsar. The central object was not a shining main sequence star. The planets were close-in low-mass worlds. Their existence was tied to supernova aftermath, accretion, or second-generation formation. This was not a slightly rearranged solar system. It was a reminder that planet formation could produce results far outside the familiar pattern. That mattered enormously once more exoplanets began to appear. In 1995, the first planet around a Sun-like star was confirmed, and it was not an Earth twin either. It was a hot Jupiter, a giant planet orbiting extremely close to its star. That discovery also shocked astronomers, because our own giant planets live far from the Sun. Together, the pulsar planets and the early hot Jupiters taught the same lesson from different directions. The solar system is not the whole template. Planets can orbit dead stars. Giant planets can hug their stars. Systems can be compact, tilted, resonant, eccentric, crowded, or strange. The universe was not waiting to provide familiar copies. It was already full of variations. Poltergeist's role in this shift is easy to understate because later discoveries became so numerous. Today, the exoplanet catalogue contains thousands of confirmed worlds, so the early pulsar planets can seem like a historical curiosity. But they were more than that. They were proof that the search was worth pursuing, and that planets could be detected with precision from Earth. They showed that careful timing could reveal low-mass worlds. They raised new formation questions. They forced astronomers to separate the concept of planet from the concept of sun-like star. A planet was no longer only something that belonged in a solar system like ours. It could belong to a pulsar system, a remnant system, a place where the word sunrise barely applies. The discovery also helped shape public imagination. Exoplanets are now part of ordinary science communication. We hear about them often, perhaps so often that the wonder can become slightly worn around the edges. But when the first confirmed worlds were announced around a dead star, the story had an eerie power. It was not only a technical result, it was an image people could feel. Planets around a dead star, a zombie planet, a ghostly family, a pulsar clock disturbed by unseen worlds. That kind of discovery makes the universe feel larger in the mind, not just in distance but in possibility. It tells people that space is not only a collection of familiar objects placed farther away, it is a place where categories bend. That public imagination matters because exoplanet science is partly driven by a very old human question. Are there other worlds? Not just other lights in the sky, but actual worlds, places, environments, perhaps even homes for something. Poltergeist did not answer the life question in a comforting way. It was probably not a place for life as we know it. It was not a blue planet under a yellow star. It was not a second Earth. But it answered the first part of the question with force. Yes, there are other worlds. They may appear in places we did not expect. They may be harsher than we imagined. They may be stranger than our first hopes. But they exist. In a way, that was healthier for the field than finding an Earth twin immediately. If the first confirmed exoplanet had looked just like Earth, people might have assumed the universe was full of Earth copies and that the main task was simply to find them. Instead, the early discoveries taught humility. The first confirmed system was a pulsar system. The first sun-like star planet was a hot Jupiter. Neither matched the simple dream. Astronomy had to adapt quickly. It had to build better theories of migration, disk evolution, planet survival, atmosphere loss, and system architecture. It had to accept that planets are not rare decorations around stars, but common outcomes of many different processes. Some processes are calm, some are violent, some are still not fully understood. Poltergeist also helped strengthen the idea that small planets are detectable. That may sound technical, but it matters. The two larger planets around PSR B1257+12 are only a few times Earth's mass. They are not giant planets. Detecting such low-mass worlds around ordinary stars is difficult because their gravitational effects are small and their transits, if they occur, are shallow. Pulsar timing offered a way to find small masses because the clock was so precise. This showed that Earth mass and super-Earth mass planets were within reach of astronomical measurement, at least in certain systems. Later, missions and instruments would make small exoplanets a major part of the field. But the pulsar planets were early proof that low-mass worlds outside the solar system could be found. At the same time, the rarity of pulsar planets taught caution. After PSR B1257+12, astronomers did not find pulsar planets everywhere. The method is powerful, but the targets are rare and the systems are unusual. That taught another important lesson. A detection method can be extremely precise and still apply to only a narrow set of objects. Exoplanet science would need many tools, not one. Pulsar timing could reveal planets around pulsars. Radial velocity could find planets around bright stars. Transits could survey huge numbers of stars at once. Micro-lensing could probe planets farther from their stars or in distant regions of the galaxy. Direct imaging could study young giant planets far from their stars. Each method would reveal a different slice of the planetary population. Poltergeist was part of the first slice, and it helped show that the whole pie was going to be complicated. A scientific pie, of course, which is less delicious but easier to publish. This diversity of methods changed how astronomers thought about bias. Every technique finds some planets more easily than others. Pulsar timing favours planets around extremely regular pulsars. Radial velocity favours massive planets close to bright stars, though precision improvements have extended its reach. Transits favour planets whose orbits are aligned so they pass in front of their stars from our viewpoint. Direct imaging favours large, young, bright planets far from their stars. If we only use one method, we may mistake its discoveries for the universe's true preferences. Poltergeist was a vivid reminder that the first things we find are not always the most common things. They are the things our tools are best suited to notice. The universe may be full of ordinary planets, but the first confirmed ones were extraordinary because our timing method could detect them. That lesson remains important today. When exoplanet catalogues show thousands of worlds, they do not show a perfect census of the galaxy. They show the planets our instruments and methods have been able to find so far. The catalogue is a map of reality, but also a map of human technique. Poltergeist sits near the beginning of that map, reminding us that discovery is shaped by where we know how to look. It is a strange little landmark at the entrance to the field, not the most Earth-like, not the most habitable, not the easiest to explain, but one of the most important because it helped prove the map could be drawn at all. The discovery changed theory as well as observation. A planet around a pulsar demands a formation story. Did it survive a supernova? Did it form from fallback material? Did it assemble from a disk created by a disrupted companion? Each possibility stretches planet formation models. Around young stars, disks are expected. Around dead stars, disks require special circumstances. The Lich system made astronomers ask whether second-generation planets could form from debris after stellar death. It forced them to model disks in harsh radiation environments, to consider rapid gas loss, dust sedimentation, compact orbital growth, and the long-term stability of low-mass planets around a neutron star. Even if pulsar planets are rare, they test the limits of the theory. They ask not only how planets usually form, but how planets can form when the usual story has been torn apart. This is one of the best uses of an unusual object. Ordinary systems tell us what is common. Extreme systems tell us what is possible. Poltergeist is not a typical planet, but it is a boundary marker. It stands near the edge of planet formation and says, the process reaches at least this far. That is scientifically valuable. If a theory cannot explain ordinary planets, it is weak. If it can explain ordinary planets but fails at every unusual case, it may still be incomplete. Poltergeist is one of those unusual cases that keeps theories honest. It asks gravity, disks, radiation, and debris to work together in a place where our intuition says they should struggle. The discovery also changed the emotional direction of the search. Exoplanet hunting quickly became connected with the search for life, and rightly so. Many people want to know whether there are other Earths, other oceans, other skies, perhaps other living things. But Poltergeist reminds us that the search for planets is bigger than the search for life. Some worlds are not homes. Some worlds are records of violence, formation, migration, and survival. Some worlds teach us about matter and gravity rather than biology. A lifeless planet can still be deeply important. It can tell us how disks behave, how systems rebuild, how small bodies survive, how stellar remnants shape their surroundings. Poltergeist may never have had a tree, an ocean, or a creature looking up at Lich with concern. It still changed astronomy. There is also a quiet human lesson in the way it was found. The discovery required patience with an odd signal. It required not dismissing small errors as meaningless. It required checking, modelling, and continuing to observe. A pulse arrived early. A pulse arrived late. The pattern repeated. That is not the dramatic image of a telescope suddenly revealing a new world in full colour. It is slower and more careful. But much of science works that way. You do not always find the universe by staring harder. Sometimes you find it by noticing that the clock is wrong in a consistent way. Poltergeist is a monument to careful attention, which is a nice thing for a planet named after a noisy ghost to become. As thousands of exoplanets were discovered later, the field became more statistical. Astronomers began asking how common planets are, how many stars have them, how common small rocky planets might be, how often planets form in habitable zones, how system architecture depends on stellar type, and how atmospheres evolve. In that large modern field, Poltergeist remains a strange starting point. It is not the answer to the main population questions. Pulsar planets are too rare for that. But it is part of the origin story of the field. It helped move exoplanets from speculation into confirmed astronomy. It proved that the techniques could work. It taught that planets appear in unexpected environments. It made the search less narrow before it had even properly begun. The name Poltergeist also continues to do useful work. Scientific names can become abstract, especially when they are strings of letters and numbers. PSR B1257+12 C, or the older designation PSR B1257+12 B, is precise, but not exactly cozy. Poltergeist is memorable. It carries the sense of an unseen disturbance, which matches the timing discovery beautifully. The planet was not seen. It was inferred from the way it disturbed a pulsar's pulse. A good name cannot replace good data, but it can help people remember why the data mattered. In this case, the name turns a technical discovery into an image, a hidden world knocking gently on the clockwork of a dead star. And so, Poltergeist changed the search for exoplanets by forcing a wider imagination. It told astronomers that planets could be found around stellar remnants. It showed that timing could detect worlds smaller than giants. It proved that other planetary systems were real before the great wave of discoveries around ordinary stars. It challenged theories of formation and survival. It reminded everyone that a planet does not need a friendly star to exist. Most of all, it removed the comfortable assumption that the first confirmed worlds would look familiar. The universe began the exoplanet era with a surprise, and that surprise prepared us for all the others. Now, after years of discoveries, we can look back and see Poltergeist not as an isolated oddity, but as the first sign that the galaxy is full of planets in every possible mood. Some orbit red dwarfs, some orbit stars like the Sun, some orbit two stars, some race around their stars in days, some drift far out in cold darkness, some may be rocky and temperate, some are swollen, scorched, stripped, frozen, young, old, or broken, and at least a few orbit dead stars, where a pulse replaces sunrise and gravity writes the planet's presence into time. Poltergeist helped teach us to expect that variety. It helped make the galaxy feel less like a set of solar system copies, and more like an enormous collection of experiments. That makes it a fitting world to carry near the end of this journey. It is not comforting in the usual way, but it is meaningful. It is a planet born from, or surviving within, a story of stellar death. It is one of the first worlds that showed us we were not alone in having planets, even if it did not show us another home. It changed the search not by being Earth-like, but by being impossible to ignore. A super-Earth in the ashes, tugging on a dead star's pulse, quietly telling astronomers that the universe had been making worlds in places we had barely thought to look. And so, after drifting through pulses, dead stars, planet-sized disturbances, and the strange little family around Lich, we arrive at the quiet thought sitting at the centre of this whole story. Poltergeist is not a comforting planet in the ordinary sense. It is not a place where we imagine soft clouds moving across a blue sky, or rivers shining under a warm afternoon sun, or some sleepy creature curling up beneath alien trees after a long day of doing whatever alien creatures do when nobody's watching. It is a super-Earth around a pulsar, a world circling the collapsed core of a star that died long ago. Its sky, if it has one, is shaped not by gentle sunlight, but by radiation and darkness. Its star is not a living yellow sphere, but a spinning neutron remnant, a dead star with a pulse regular enough to reveal planets by the tiny errors they make in time. And yet, even in that harsh setting, the lesson of Poltergeist is not only about danger, it is about persistence. It's about what can remain, what can rebuild, and what the universe can do with the material left behind after an ending. At the beginning of this journey, Poltergeist sounded almost like a haunted object, and in a way that name has been useful. A poltergeist is known by disturbances. Something unseen moves, something knocks, something makes itself known indirectly. That is almost exactly how this planet entered astronomy. It was not photographed as a bright dot beside a star. It did not pass in front of a warm sun and dim the starlight for a waiting telescope. It revealed itself by tugging on a pulsar, by making the dead star's radio pulses arrive a little early and a little late. That is such a delicate form of discovery that it feels almost impossible at first. A planet several times the mass of Earth, orbiting hundreds of light years away, known because it shifted the timing of a dead star's pulse by tiny amounts. If that were in a story, it might sound too convenient. In science, it was a measurement. The ghost had gravity. That alone would make Poltergeist memorable, but the planet's deeper meaning comes from where it is. A pulsar is not a normal star in old age. It is the compact remnant left after a massive star collapses and explodes. The star that came before Lich did not fade politely. It died violently. Its core fell inward. Its outer layers were thrown into space. The result was a neutron star, an object so dense and extreme that our everyday comparisons always feel a little inadequate. A city-sized remnant with more mass than the sun. A spinning magnetic object sending beams through space. A clock born from catastrophe. Around that, Poltergeist moves. Around that, Draugr and Phobator move too. The system looks like an ending that somehow became an arrangement again. This is why Poltergeist is often called a zombie planet. It belongs to the afterlife of a star. The phrase is not a formal scientific label, of course. Astronomers do not have a neat official box marked zombie planets, although one has to admit it would make catalogue browsing more dramatic. But the phrase captures something real about the system. Poltergeist exists where ordinary expectations might have said planets should not be. If it is a survivor from before the supernova, then it endured one of the most violent events a planetary system can face. If it formed afterward, then it is even more like a second life, a world assembled from debris after the central star's main story had already ended. Either way, it teaches us that endings in the universe are not always clean stopping points. Sometimes they are transitions. Sometimes they destroy one structure and make the conditions for another. That may be one of the most important lessons astronomy has to offer. The universe does not treat destruction as simply a blank space. A star dies, and heavy elements are scattered. Gas clouds are stirred. Shock waves compress material. New stars may form later from enriched debris. Planets gather from dust that came from older stars. Earth itself is made from recycled stellar material. The iron in rocks, the calcium in bones, the oxygen in water, the carbon in living things, all of it belongs to a long history of stars forming, living, dying, and returning material to space. In that broad sense, every rocky planet is made from old stellar ash, but Poltergeist brings that idea closer to the surface. Its connection to stellar death is not hidden deep in the ancient ancestry of its atoms. It orbits the remnant directly. It lives beside the evidence. The small family around Lich makes this even more powerful. Poltergeist is not a lonely exception drifting by chance around a dead star. Draugr, tiny and close in, and Phobator, another super-Earth farther out, share the system. Their orbits form a compact arrangement, and the two larger planets are close enough in their orbital relationship that their mutual gravity helps confirm the structure. This is not just rubble scattered randomly around a neutron star. It is an ordered planetary system, small but real. That order matters. It tells us that after violence, gravity can still organize matter. It tells us that disks can form in unexpected places, that particles can settle, that worlds can grow, that stable orbits can emerge from a history that was anything but stable. Of course, this does not mean Poltergeist is safe. Survival in the universe does not always mean comfort. A rock can survive where a flower cannot. A planet can persist where an atmosphere may be stripped away. An orbit can remain stable while the surface below is battered by radiation. When we use the word survival in this story, we have to be clear about what is surviving. We're not talking about a living world, at least not based on anything we know. We're not talking about forests or oceans or a place where biology is likely to be quietly waiting for company. We're talking about the survival of matter, of structure, of planetary form. Poltergeist teaches us that a world can survive or be rebuilt without being kind. That is a harder kind of lesson, but an honest one. There is something humbling in that. Humans often connect survival with warmth, safety, and memory. We think of a house still standing after a storm, a tree growing again after a fire, a person carrying on after a difficult year. The universe has a wider and colder definition. It lets a planet circle a pulsar in darkness and calls that survival too. Poltergeist may not be alive, but it persists. It keeps its orbit. It pulls on Lich. It participates in the timing signal that reaches Earth. It is not comfortable, but it is present. Sometimes presence is the first and most basic kind of survival, and that presence changed astronomy. Before the great age of exoplanet discoveries, before thousands of worlds filled NASA catalogues and scientific papers, Poltergeist and its siblings proved that planets could be found beyond the solar system. Even more surprising, they proved it in a place no one would have chosen for a gentle first example. The universe did not introduce us to exoplanets by showing us another Earth under another sun. It showed us planets around a dead star. That was not the easy answer to the old question, are there other worlds? It was a stranger answer, but maybe a better one. It warned us immediately that other worlds would not simply be copies of home. They would include the scorched, the frozen, the swollen, the stripped, the hidden, the orphaned, and the worlds moving around remnants of stars that no longer shine in the usual way. That is one reason Poltergeist still matters in a time when thousands of exoplanets are known. It is not the most habitable. It is not the most picturesque. It is not the kind of place we would choose for the first postcard from another solar system. But it sits near the beginning of confirmed exoplanet history, quietly reminding us that the galaxy was strange before we had the tools to see it properly. The planet told astronomers to widen the search. It said in its own silent gravitational way that planets could appear in places that seemed unlikely. It helped teach us that a planetary system is not defined only by a warm star and a familiar order. A planetary system can also be a pulsar, a few compact worlds, and a radio signal that carries their existence across space. The way Poltergeist was discovered also says something about patience. There is no dramatic image here, no glowing portrait of a world with clouds and continents, just pulse arrival times, tiny deviations, a clock that was not wrong randomly, but wrong in a repeating way. Astronomers listened to the pattern and realized that the timing errors were not errors in the ordinary sense. They were the pull of planets. This is such a quiet kind of discovery that it almost feels like a lesson in how to pay attention. The universe often speaks softly, not because it is trying to be mysterious, but because distance makes everything faint. A planet around a pulsar does not announce itself with a sunrise. It changes a number, it adds a wobble, it makes a signal arrive late by a sliver of time, and from that sliver, a world can be found. For a listener settling down in the dark, there is something oddly soothing about that. Not because the planet is gentle, but because the method is. Pulse after pulse, measured over time, a careful record, a repeated pattern, a hidden cause slowly becoming clear. It is a reminder that understanding does not always arrive all at once. Sometimes it comes from watching carefully, returning again, noticing what keeps happening. Poltergeist was not found by rushing. It was found because the pulse was timed and timed again, and the difference mattered. There is a quiet patience in that, a patience that feels very different from the violent origin of the system itself. The dead star at the centre, Lich, also changes how we think about stars. We often treat stars as sources of life and light, which they can be. The sun is exactly that for Earth. But stars are also engines of change. They make elements, they lose mass, they explode, they leave remnants, they shape the conditions for the next generation of objects. A star's death can be terrible for anything nearby, but on larger scales it is part of the reason solid planets exist at all. Without earlier stars dying, there would be no heavy elements for worlds like Earth. Without cosmic recycling, there would be no rocky ground under our feet. Poltergeist makes that recycling visible in an extreme way. It circles the leftover core, as if refusing to let the story end at the explosion. Perhaps that is the central thought to carry from this system. The universe is not built from neat beginnings and neat endings. It is built from transformations. A cloud becomes a star becomes a remnant gathers material. Material becomes planets. Planets may be broken, stripped, or scattered. Their pieces may become something else. Time does not preserve everything, but it does not waste everything either. It changes the form. Poltergeist is a world shaped by such change. It is not proof that every disaster leads to renewal, because that would be too simple. Many disasters simply destroy. Many systems do not rebuild. Many planets are lost. But Poltergeist proves that renewal can happen in places that seem deeply unlikely. That idea does not need to be made grander than it is. We do not have to pretend Poltergeist is a hopeful planet in the human sense. It is probably a harsh world in a harsh system. It may be airless. It may be radiation battered. Its sky may be black. Its surface altered by particles from the pulsar. Its year shorter than one of our seasons. It may never have known anything like rain, waves, leaves, or a soft wind across open ground, but it is still a world. It is still a product of matter gathering into form. It still moves with its siblings around Lich. It still carries a history that reaches back through stellar death and forward through every orbit it continues to complete. In that way, Poltergeist teaches a different kind of cosmic survival. Not survival as comfort, not survival as life, survival as pattern, survival as matter remaining in motion, survival as gravity finding order after violence, survival as a planet becoming detectable across the galaxy, because it refuses, in the simplest physical sense, to have no effect. It pulls, it orbits, it changes the timing of the dead star, it leaves evidence. That may be a cold kind of survival, but it is real. And it also changes how we look at home. Earth feels very far from Poltergeist, and not only in distance. Earth orbits a stable middle-aged star. It has an atmosphere, oceans, a magnetic field, weather, and life. It has mornings, seasons, and the small daily rituals that make time feel human. Poltergeist has none of those comforts that we know of. Yet both worlds are planets. Both are made from cosmic material. Both obey gravity. Both belong to the long story of stars making and remaking the ingredients of the galaxy. Comparing them does not make Earth seem less special. It makes Earth seem more precious. We live on a planet where survival did become comfort, and eventually life, thought, and the ability to listen for pulses from dead stars. That is not ordinary. That is a rare kind of kindness from physics, chemistry, and time. So if there is a gentle final lesson here, It may be this: the universe is wider than our ideas of usefulness. Poltergeist is not useful because it is habitable. It is useful because it teaches us what planets can be. It shows that worlds can exist around the remains of stars. It shows that planet formation can be stranger than the nursery story we first imagined. It shows that a dead star can still have companions, that a system can be rebuilt from debris, and that the first confirmed exoplanets could come from a place that looked more like an ending than a beginning. It reminds us that the universe is not only a collection of homes, it is a collection of histories. And now, dear listener, we can let the scene settle, somewhere in the direction of Virgo, far beyond the reach of any bedtime window. PSR B1257+12 continues to spin. Its beam continues to sweep through space. Its pulses continue their long outward journeys. Around it, Draugr moves close in. Poltergeist follows its 66-day path. Phobator circles farther out. They do not need to be seen to be real. They do not need sunlight to keep moving. They do not need us to name them, though we have, because humans are very good at naming the strange things we find in the dark. If this journey has brought you a little calm, or given your mind a quiet place to wander, I would be grateful if you liked the video, subscribed, or shared this sleepy corner of science with someone else who might enjoy drifting among the stranger worlds of the universe. And if you are still awake, perhaps take one last moment to notice where you are, the room around you, the time on your clock, the little patch of Earth holding you safely under a living star. Far away, a zombie planet orbits a dead one. Here, for now, you're held by a world that survived in a warmer way. A world with air, darkness, rest, and morning waiting somewhere beyond the night. Sleep well, fellow traveller, wherever you are listening from, and may the thought of Poltergeist remind you that even after the brightest stars are gone, the universe still has ways of keeping time.